And I think we're live. Hello, everyone. Welcome. Today we're going to do day 10 of Advent of Code. I'm basically learning Rust, except for one day, which I was tired of a bit of Rust, and then I did Python. Today we're continuing the Rust tradition, and let's dive in. So we are day 10, Pipe Maze. You use the glider to ride the hot air from Desert Island all the way up to the floating metal island. This island is surprisingly cold. There are definitely aren't any thermals to glide on. So you leave your hang glider behind. You wander around for a while, but you don't find any people or animals. However, you do occasionally find signposts labeled hot springs, pointing in a seemingly consistent direction. Maybe you can find someone at the hot springs and ask them where to find the desert machine parts are made. The landscape here is alien. Even the flowers and trees are made of metal. As you stop to admire some meadow grass, you notice something metallic scurry away in your peripheral vision, and jump into a big pipe. Didn't look like any animal you've ever seen. Um, if you want a better look, you'll need to get ahead of it. Scanning the area, you discover that the entire field you're standing on is a densely packed with pipes. It was hard to tell at first because they're at the same metallic silver color as the ground. You make a quick sketch of the surface pipes. You can see your puzzle input. The pipes are arranged in two-dimensional grid of tiles. Vertical bar is a vertical pipe connecting from north to south. Horizontal bar is connecting from east to west. L is a 90-degree bend. J is a 90-degree bend. Okay, so we've got vertical 90-degree bends. Dot is ground. There is no pipe in this tile. And S is the starting position of the animal. There is a pipe on this tile, but your sketch doesn't show what shape of the pipe has. What? I need to read that again. S is the starting position of the animal. There is a pipe on this tile, but your sketch doesn't show what shape the pipe has. Based on the acoustics of the animal's scurrying, you are confident the pipe that contains the animal is one large continuous loop. For example, here this is a square loop of pipe. If the animal has entered this loop in the north west corner, the sketch would look instead like this. Okay. In the above diagram, S is still a 90-degree tile bend, a 90-degree bend with the letter F. You can tell because of how adjacent pipes connect to it. Interesting. Unfortunately, there are also many pipes that aren't connected to the loop. This sketch shows the same loop as above. By the way, I see there's someone watching. Hi there. So yeah, here we've got like a lot of pipes that aren't related to this sketch. And how would we know that? Because as you can see, this right angle thing, this 90-degree bend cannot lead to this S, and also this L cannot be lead to this S. Yeah, we can still figure out which pipes form the main loop. They're the ones connected to the S pipes. Yeah. So pipes every pipe in the main loop connects to two of its neighbors, including S, which leaves exactly which will have exactly two pipes connecting to it, and which is assumed to connect back to those two pipes. Okay, here's a sketch. Oh, sorry. That contains slightly more complex main loop. Here we've got, let's look at that. We've got the start. This is a 90-degree bend. Yeah, so we go from here. We can basically we can trace it out. Okay, cool. So we can trace this thing out. There's also an example sketch with some extra pipes that are just tiles without like the same loop, but with more gibberish around it. If you want to get out, out ahead of the animal, you should find the tile in the loop that is farthest from the starting point, because the animal is in the pipe. It doesn't make sense to measure this by direct distance. Instead, you need to find the number of steps we need to take along the loop. Okay, to reach from the starting point, regardless of which way around the loop the animal went. So in this case, we've got, yeah, exactly. Yeah, we can basically mark the amount of steps it takes, and we should find a maximum. This also implicitly claims that this number is either it's even, because we've got 0 once, and then all of the other numbers we should have twice, and exactly one maximum. Yeah, okay, so this is going to also, like, this is an interesting assumption. Find a single giant loop at the starting of S. Starting at S, how many steps along the loop does it take to get from the starting position to the point farthest from the starting position? How many steps along the loop does it take to get from the starting position to the farthest? Okay, so we just need to find the maximum distance within the loop. So let's just do that. We don't actually need to construct the full loop. We just need to travel along it and find it. So we start with S, and then we infer which of the neighboring positions have are actually pointing towards S, and then we just pick one, which doesn't really matter. We can just always go left. Really doesn't matter. And then we just walk until we find the maximum number. And just for just so we will be able to break, we can either always keep track of what was the previous number we've seen, or just go along the whole thing, and then just take the maximum. Both of them should work. And actually taking the maximum also means that we are definitely going to work. This is also going to work even if we've got two ways to travel around the loop. Oh, interesting. Let's think about that. Is this always an even number? No, it's not always an even number. Because if we have no, actually, maybe it is. Interesting. Could that be not an even number? I'm guessing it could. Yeah, we could imagine a loop that is divisible. Yeah, okay. So it's not about like it doesn't need to be even. Anyhow, let's just start going. So we've got where is this? Yeah, so we've got like this junk thing here. And we can actually, okay, let's start simple, which is this one. This is the simple map. Okay, so let's hop onto Rust Rover and start coding. Oh, sorry about that. I have a thing that I need to do very quickly. You got it. Okay, and I'm back. Just needed to provision machine for something. Anyhow, back to coding. So we've got this thing. We can duplicate our day 9 solution and then start doing more stuff. So we've got day 9. We can attach this, not day 9, we've got day 10 now. We can attach that to our main module. We should also have day 10 at this point. That's going to be day 10. And we just need to actually have that here. Okay, so we're done with scaffolding, I think. And we could start writing things. So first of all, we need to walk this map. And how would we do that? We need an enum of all these things. So let's start with creating this enum. So we've got pipe, and that is going to be, well, vertical, horizontal. We've got bend. How they define these? So we've got bend northeast. Okay, so yeah, okay, so let's actually have that. So instead of that, this should be north south, east west. Then we've got northeast. Why am I northeast? Oh, yeah. North south, east west, northeast, northwest, and then we've got southeast, southwest, and we've got nothing, which is the ground, and we've got our starting position. And start. Okay, so I think this is our ground. Let's call that ground. So these are all the possible values that we've got for our thing. By the way, is this accidentally 8 lines? 7. Wait. Okay, so that's 8 lines. Okay, so this could have been also like a very compact U8. But I don't think we need performance for this. If we look at the input, then this probably isn't going to be gigantic. Yeah, we don't need to do anything compact here. This is small enough. So basically we need to load this into like a big ass map and then find the start. And once we find the start, we need to poke around the neighborhood, see which one is connecting, then do the trace, then do it from the other round, and then we could find the maximum by, yeah, basically find the maximum. So yeah, let's try and do that. We've got our pipes. Now we can try to build up a map. So the map could either be like a very big vector, or we could just have it as a graph, basically, because we could. Having it as a graph is actually more intuitive in the sense that things aren't always really square, let's call that, and we just need to traverse the map somehow. So, okay, so let's try to build this as as a hash map, basically. So we do want our type, which is going to be our, not reading, but how would we call that? This is kind of like, yeah, a maze, but also, yeah, this is going to be a graph, basically. So our graph is not going to be a vec of pipes, but a hash map from pipe to pipe. It's not going to be pipe to pipe, it's going to be a location to pipe. So we've got our coordinates. So type coordinates. And I know we could actually use two-dimensional grid for this, but I think this is actually going to be way more useful to traverse this as a graph than to traverse this as a linear walk-through memory, because we are not going to do any linear walks here. We're going to basically, anyway, randomly jump around. The use of array is very good if we'd want, let's call that like very like compact, a compact view in memory, but usually that's not where like the problems lie in terms of performance. So I'm avoiding this optimization. If we see for some reasons things are slow, then we would need to figure this out. Okay, so first of all, this is our like data model. We do want to walk the loop. So let's actually just so we do want like a way to walk the graph. So we want some kind of graph, which is going to be a borrow of the graph. We don't need to own the graph. And we do want our starting point. So yeah, something like that. That should do it. So this is our walk, and this is going to what step? No, this is actually looping and getting to somewhere. So we could actually also keep some kind of predicate here. So that would help us. Let's think about that. How do we want to walk this graph? So how like we are going to walk through everything. We would like to somehow understand where do we want to actually like where do we want to step into and when do we want to stop. So maybe we just want to, this is going to be basically just a step. So let's actually just step through the graph once. And so we've got a coordinate and we are going to return a coordinate back. So this is going to be our step. And stepping through the graph is basically this thing, but we do want to infer the start. So northwest, north-south is going to keep the same x. So yeah. Let's actually have that as a y x plus 0 and plus 0, and that is like more. So yeah, ground is basically this should be unreachable. We should not be able to like ground is not a valid type, and also start is that would be an infer start. So infer direction, graph coordinate, and that's also going to be another borrow. So how do we infer the start direction? So the function infer start direction is also going to receive the same borrowed graph and another coordinate. And why is it borrowed, by the way? This shouldn't be borrowed. There is no need for this to be borrowed. This is so small. Oh, I see. Maybe because it's a tuple or whatever. Okay, so we've got that. We are going to return a coordinate, which is, look at that. So for a start pipe, we do want to infer this direction, which is we need to match on the neighborhood. So we do need to look in 4 directions and then do something about that. So we have our start. So infer start directions. Interesting. So this also means that we could always go like front to like we could go to in both directions. So we need to think about like which one is it. So we cannot just use we cannot just like have that. This is not correct basically, because this is actually only enabling us to traverse in like one direction. So we should say prev, which is our previous type, And so we came from something, then we should go to something. So how do we pass that correct? How do we do this correctly? Let's think about that. So we've got our graph, which is basically our state. Could like implement that in some sense, but whatever. So we've got our previous pipe, and if we look at let's actually literally just do this like on a calligraph. So we've got some pipe, and then we advanced into another right angle pipe. So we have our coordinates of whatever that's going to be 0, 0, and that's going to be 0, 1. So in order for us to know which one can we actually use, like there are basically two options, and we need to just not walk back, basically. So instead of walking back, let's actually, okay, so we do have two coordinates. So we've got basically prev coordinate and current coordinate. So for each type of coordinate, we do have two options, and we need to match the one that's not us, not the previous one. So let's just implement that. Okay. So we can match. Okay, so there's a lot of like combinations, but we just want to basically infer the possible directions. So um, so let's try to do this. We've got what could be the next? The two next options basically. So Fn next chords. This is going to receive a graph and not a vec, but a tuple of two options. So chord. Yeah. For each one of these, this is now this should now be very simple. So we say, yeah, we are getting this. This is, let's actually have that as an optional. So this is, that way we won't need to unwrap everywhere, just to be sure. That's like a better way to do this. Okay, so we've got, yeah, this looks good. Let's just make sure that actually Copilot is not like bullshitting us. So on north, south, we've got x plus 0, yeah, in both cases, and y is going to be, yeah, plus minus 1, and the east-west is going to be the same way. The northeast is either going to be, let's think about that. No, this is a diagonal. This is definitely wrong. So it's either going to be x plus 0, y plus 1. Or x plus 1, y plus 0. Is it plus or minus? Because we need to go north. So north is actually minus 1. Right? Because north is actually decrementing y. So north is going to be, yeah, east. And north is going to be minus 1, and east is also going to be going left. So, right, what? No. East is, this is north, east. Okay, so east is +1. So that's going to be x plus 1. Then we should say northwest, and that is going to be, again, north is x plus 0, y minus 1, and that needs to be x minus 1. Yeah, that's very good. Northeast is going to be, southeast is going to be this transition. Okay, so south is going to be +1, yeah, and east is going to be, okay. And so I think this table is ready and only this one is not. So our start thing is actually going to be very annoying because, well, we do need to look at the neighborhood. So let's actually try to do that. So directions. So in first start, that's going to be like the hard thing to actually compute for a minute. So let's do that. We could say in first start is actually we are getting our start thing. Start is not a valid pipe. Yeah, that's actually correct. But we do just want to look in all. Okay, so we do want let up be down. Sorry, let's actually call that north south. Okay, so let north be this, south be this, let south. Wait, why is north? North is -1. Copilot is so stupid sometimes. So we've got east is +1, that is correct, and west is -1. And then if so for each of these, we are going to now look at the next coordinates of each of these because we are going to we do need to basically find the two pairs that have that. So so firstly we do want, yeah, if graph contains key, that's still not good. So this should be still a pair of coordinates. Oh, actually, you know what? This is actually a thing which we just need to, so we just need to infer the pipe type. So infer pipe. So we just want to return the pipe type, and then we can use the same algorithm, which is the infer coordinates on that pipe type. So we just need to return a pipe. Infer start pipe. So we've got a graph, a coordinate, and now on the graph, we want to, instead of like doing this, we should say something like, for each of these, we do want to do something. All of these are just the coordinates. And north get option, yeah. Basically, we just want all of these. And let so we don't actually, yeah, we just need to say next coordinates on this thing. So yeah, graph north coordinates. Okay, so this should give us the next coordinates on everything, except for the fact that we still need to make this an option. So let's actually have that as an option, and that should be Yeah, so it's either that or we can match on that. And if it's some, oh, we could actually maybe, is there like a cleaner way to do this? Let's think about that. So this is a thing. So it might be okay. So it's some. It's some pipe basically. So graph on this thing, it's some pipe. And if it's none, then we are returning none, and this should also be returning none. And all of these should return some coordinates, so some. And it says that, okay, there's definitely a better way to do this, like when, instead of like doing all of this something, but seems like I'm missing one more parentheses here. Yeah, okay, and this should be infer start, and the infer start should also by itself be some pipe. No, so actually infer start pipe is, okay, let's do this quickly. So we've got all of our next coordinates. Let's figure this out. And each one of these, we should match on that and like find if our original coordinates are here or not. And if it's in both in two directions, then we know what the type of the pipe is. We could make assumptions that there is exactly two pipes here. So damn, that's not a thing. Because okay, so let's figure this out. So first of all, for each one of these, we do want to do something, which is to figure out if, yeah, we can match on north. Then if it's is there like a nicer way to do this? I basically want to inverse this thing. Okay, so in order for us to inverse this thing, we need to map the north coordinates to its pointing things. So let's think about that. Could we get that just by the pipe type? We don't need to actually do like any crazy stuff. So let's actually just do this with the pipe type directly. So instead of that, we could graph dot get this thing. Don't need to do anything fancy here, or we do. Okay, so we've got an optional pipe. Okay, so one of them is should actually be, like, two of them should be valid. Must be valid. So which one of them is valid? We don't know yet. So let's think about that. We can match on all of these, and we do have like we would have some kind of structure. We probably won't. So first of all, we can assert. No, we cannot assert anything at this point. We need to find the two that's actually that are actually pointing towards us. So how do we do that? We've got our start. We need to probe right. If it's pointing at us, then we should use it. Otherwise, not. So let north connected going to be match on north, and then if it's some north, okay, that's actually useful. Okay, so if it's north, south, or northeast, no, that's actually southeast, or southwest. Yeah, okay, so it can be any of these. Is there like a shorthand way to write all of these, like collapsing all of these into something? Probably not, but then we can say south connected, and south connected is north south, northeast southeast, yeah. And east connected is, let's just verify that. So we've got either east west or northwest or northeast, yeah. So now all of these, first of all, yeah, cert north plus all of these equals 2. And can we assert that easily? No, because it's all booleans, and why should booleans add up in Rustland? Cannot add so now that we've got all of these, we can match on all of these. Okay, so it's either, yeah, we should have like 4 structure, not 4, 6 options here. So it's either let's literally have the full truth table. So we either have true, true, that's going to be north south. We've got east west, northeast, and northwest, southeast. Wait, what? No, false. True. And then yeah, southeast, and anything else invalid start pipe. And it says that unreachable pattern. Why is that? Because this should be false. This should be true. And also here, this should be true. This should be false. So we've got north, east, northwest, southeast, southwest. So these are all the valid pairs that we've got. Anything else is invalid. And we should maybe, just to be nice, we could like format this. So let's we could format this as invalid start pipe, and yeah. Is there like a nice way to like do this? Yeah, never mind. We get to this unreachable thing, then we know that something has gone wrong. We should probably probe this, like we should unit test this very soon. And now that we've got our pipe type, we could do this. So we should say not step, but where's this? Our next coordinates is going to be the next coordinates of the infer start pipe. And this thing should also accept the graph as a thing, and this is now this is a pipe. So how does it know what to do? It does not know what to do. We need to Yeah, okay, so this should not return the pipe itself, but actually infer start coordinates is just, okay, so basically fn infer start coordinates. That's going to be the graph. No, why you must be so stupid? So that's going to be a chord, and that's going to return a pair of coordinates. Oh, so not coordinates, but yeah, start directions. Directions. That's going to be let pipe be infer start pipe, pass in the thing. Then we just return the next coordinates of the graph and the pipe. So this one does not actually do anything fancy. So this one just needs, this should just get the pipe, which is already a pipe, and that might be, well, we could literally do this. We just match on the pipe. We don't need the graph even. Or let's actually tag it along just to be sure. So we could match on the pipe, and we don't need the whole something. We've got our coordinates, our pipe. This is like redundant information, which I don't like, because this is actually not the source of truth anymore. So how do we tag along? We could mutate the start coordinate, actually, and then we don't need to think about it. So the start coordinate is actually, yeah, we should, let's consider that as unreachable when we actually compute the next coordinates. So we've got, let's remove all of this. And all of these. Okay, so you know what? Look, let's keep the options. So that's an option of this pair. So everything else is none. Next coordinates. So yeah, we only support these things, and this one does not do anything with the graph at this point. So next coordinates is just the, well, next coordinates. So what we want to do is basically return, once we know the pipe type, we can replace it and just keep track of like where to start. So that we won't like have anything crazy to do with the graph itself. We just want to know like what entry point should we start with. Yeah. So we've got like how we know how to infer the start pipe. We should test that in a minute. We know what the start direction is. We don't need to know that because we just know the next coordinates for a given coordinate in pipe. And that is either an optional 2 coordinate or nothing. We do not need to know anything about that. We just, oh, we could literally just not keep track of X and Y and just literally return like the offsets and then add them up. So, no, but that's actually a nicer computation. So yeah, let's just keep that local. So we've got our previous coordinate, our current coordinate, and all we want to do is want to know like what should we step into and from to the graph. So these ones should be unreachable. Okay, so our current is this thing. So let's just clean this up. So we've got, well, let next the next coordinates on the graph get current unwrap clone. Ooh, that's harsh. This could be reference. We don't need to do anything fancy, so we could just have that. And if we get this as an option, then we're already returning options. So yeah, no losses here. So this is an optional. Is it a ref option or an optional ref? It's an optional ref. Yeah, okay, so we've got an optional reference. And this thing returns us the next options. We can match on them, so let's do that. So we've got match sum. Actually, match on next. If it's sum A and B, if A and B equals prev. Yeah, okay, so this is a thing, and none is, well, invalid pipe. Yeah. But we could have that also as an option because we are on a roll here. And that should be basically just none weights to none. So there's probably a better way to do this. Found coordinates, because that should be some coordinates. Sum B, sum A. Is that a thing? I think so. I think that's okay. So this is now a step in some direction. Okay, so we've got like the walking thing sorted out, but this now is an option, so it's either, yeah, it's some northwest. This thing should be a result of a pipe, and that way we don't need to panic. And that's going to be an anyhow result because this is, well, the way to do things. And then we, instead of like doing unreachable stuff, we could say anyhow, not bail. Anyhow, unable to infill pipe. And then this thing should also be okay something. And this one, why is it unhappy? It says that cannot determine the resolution macro of anyhow. Anyhow, if no input resolution is stuck, try simplifying the macro inputs. So is that just not the way to do this? Anyhow, I'm not sure if that would compile or not, but we will figure this out quite soon. So we've got that. We've written everything that we need to write, I think, in order to walk everything, but we do not yet. We yet do not have like a way to actually like get something out of the thing. So we only we're only stepping and we're getting the next thing, but we are not doing like any iteration or smart thing with that information. So let's clear out all of this crap because we don't need any of that. We need to start parsing, which is the usually like where we actually start. So test part 1. First of all, we do want our reference map. So let's just have it. So we've got 2 references. So let's start with this thing. Where's the simplest one? Yeah, so that's the simple one. So we can paste it in. And we should expect this to equate to, what was it? 4. So this should be the thing. And then we've got another assertion, which is we should use also this one, which just has more junk in it, but it's the same map. Wait, this is the one. Okay, yeah, this is the same map. So we've got another let input, which is this one. Should equate to 4 as well. Yeah. And we've got another input, which is this thing. This is the clean but longer pipe. Let thing be this thing, and that should equate to, what was it, 8, I think. And then we've got the junkified thing. And the junkified one should equate to, so yeah, let input be this thing, should also equate to 8. Okay, and test part 2, that's going to be a to-do. Amazing. And we should delete all of that because we don't know yet what part 2 is. So let's start parsing. Oh, this one is obviously also a bunch of to-dos. So to-do. Let's parse the maze. So we do want something like that. So test function, test parse graph. And we do know exactly what we are aiming for, which is this thing. So let's just paste it in again. And that is going to be on Copilot. No, of course not. So this is our input, and we've got an assert equal something, and we'll handle that in a minute. But I really want to close the brackets. Okay. So we could say let actual equal parse graph, and we don't have the parse graph thing yet, but that's very good. And we've got our expected. So what is going to be our expected thing? So our expected is going to be a graph from eta of a vector that contains a lot of crap. So, damn. So the coordinates should start with 0, not with 1. So let's just try to let Copilot understand that by saying this thing, and that's a vec of a tuple of I32 and pipe ground. Let's figure out if this is actually correct. So we've got 0, 0 is actually ground. 1, 0, that's X. So you know what? Oh, I see. So we've got another row which is empty. Okay, so that's actually correct. So 0 through 4 is ground, and then 0, 1 is ground, and then 1, 1 is not ground. 1, 1 is north, southeast, southeast. Oh shit. That's going to be ground. This one is southeast. And then let's look at that. We've got 2, 1, which is east-west. Then 3, 1, which is southwest. So southwest. Then 4, 1 is ground. Okay, so we definitely want to remove all of this crap because obviously Copilot doesn't know what it is doing. And 4, 1 is actually a thing. So yeah, let's duplicate that. 4, 1 is a ground. Then there's probably a better way to like make this assertion correct, but I mean, we could literally serialize and deserialize this thing, and then that could give us like a very nice assertion. But we aren't meant to have such nice things. So let's continue on with this. Actually, you know what? Let's just pass a smaller map. This should just be a thing. So let's just start with literally just ground. This should be like the simplest and dumbest thing to assert. Then we could say expected equals actual, and then we could have another thing to pass, which is this thing. Let's call that, and then we can also like have \n, and then that could be something. Okay, so let's just have that. So we've got pipe comma pipe, and then this should be a lot nicer to pass and actually useful. So we've got that. We can pass the graph. I mean, we can make believe pass the graph. Then our expected is going to be the same thing, which is graph from something. Seems like Copilot is like really really into trying to make this work. So let's give it a little bit more from iter. Then we say vec of lot of pairs. So we've got 0, 0, comma pipe. What is it? Here it's going to be south. Then we've got east west, and then basically this should be it. So that should conclude like the most basic kinds of parsing. I think this is now a very nice test. We should be able to like parse that. So let's try parse graph. This should return, first of all, it gets an input ref star, and it returns an I result of ref star and well, a graph. So that should be a thing to do. And we've got many one, not many, many fold many one. And we do want to fold multiple hash maps together. So let's figure this out. We've got a separated list by new lines. That's actually a thing. So we've got a new line and we've got not many one tag. No, that's just stupid. Okay, so here we've got a to do. We need to pass also like the small thing. And fold many, we do want our graph new. And we need to, we've got our mutable accumulator. And we've got our item, which is now going to be vector because it's a separated list. No, so that's actually going to be another fold because we are going to fold many things into the same something. So we want to fold we want we need to linearize everything. So it's either interesting. So we might not actually need to but we want our what's its name? We want our x and y coordinates. So let's figure these out. So actually separated list is going to be useful, I think. Okay, so let's think about that. Interesting. So we might want to actually have that as a two-dimensional vector when we're passing it, then we should like traverse the actual x and y coordinates and convert that into a graph. So let's do that. So we've got a separated list. So first of all, that's going to map into a graph, but that's a problem for another thing. So separated list by new lines. That's our outer list. And we've got an alternative, which is a thing. We should import map, yeah. Knowing hell everything here is correct. We do want alt anyone. Yeah, okay, so dot is gram, north, south is bar, and east, west is dash, northeast is j, if I recall correctly. So that's actually not a tag. This should be like a char, basically. So parser char. So this should be a dot. Always like a one-dimensional thing. So this should be a char of. Oh, we could say one of instead of alt, right? This is maybe like the better way to do this. One of. Oh, but that doesn't let us map it easily to the thing. So we could say char, yeah. And that is going to be northwest. And let's just do this. East-west, yeah. And this is not correct. This is going to be an... What is the actual like mapping here? We've got F as the southeast. As southeast. We've got 7 as southwest. Got L as northeast. And we've got J as northwest. Are these all the things that we need to worry about? We've got start. So we've got map star s start. And I think this concludes the thing. So we've got a separated list of many of these. So we should now have a vector of lines. So let's figure out what we could do with these lines. Yeah, so we've got a vector of pipes. And we could, well, fold that into our thing. So let's do that easily, quickly. So this is a thing. And we are missing passing the input. And this thing should be a graph now. So we could just do this. So we could say, not, could we fold it? So we should like do the double iteration basically, and then fold everything into into a whatever, what's its name? Into our hash map. So we should say enumerate, and then oh, we should actually, yeah, enumerate and not fold yet, not yet. This is our lines. We need to flat map that. And then we've got our y coordinate. Yeah, that's actually correct. And we've got our line, and each line we are enumerating. We've got our x. And we are... So we should, at this point, let's figure this out. We've got line, enumerate. We've got our x, and we've got our y coordinates. But we do need our thing as well. We do need our pipe. So that's going to be pipe. And that's going to be a reference. And in order for that to work, we need to fold that. Oh, we could literally collect that. So collect. And that should work. Let's figure out if this actually would compile. So first of all, let's just build that, and then it says cannot determine the resolution import, so use anyhow. Interesting. So should we do this? How do we use anyhow correctly? Anyhow thing. Okay. So use anyhow, and that's our macro, right? Okay, so now instead of using it like this, we just say this thing, right? Then it says, yeah, okay, match has incompatible types. And now we've got into, okay, so we've got expected result type error, found error. Interesting. So that way. Okay, so now we're going deeper into this thing. So we've got instead hash map cannot be built from iterator ref. Ooh, that's the reference thing. Okay, so we should say dot clone, and that should do it. Or is it cloning the reference instead of the thing? Okay, so we should, instead of clone, we should say style. And then it says equal, because not applied to the right thing, and we should say that, well, it's actual dot question mark, and then it will complain that this thing is, well, anyhow result something, yeah, should maybe work. Then it says the question mark operator cannot be applied to refs the hash map. Oh, it's already unwrapped. I see. So that should be this thing dot dot one. So that's our graph. So we don't need to do any question marks on this thing. And then it says partial equality. Yeah, we could say that. And then it's going to also complain that we don't have debug because I already know this thing. Then it will also complain probably on the next line, which is, well, I want also here to, yeah, question mark and unwrap. And then it says expected enum result found unit. So we could return, okay, unit. Move occurs because pipe has type which does not implement copy. I mean, okay, so let's implement copy. This is very much copyable. Copy, clone. Then it says closure returned here. So instead of that, let's clone. Or should it be something like this? Y is borrowed here. Interesting. So also Y, what is it with like references? These are integers. Just give me a copy of the integer. Clone dot clone. Then it says Y is borrowed here may outlive borrowed thing. So if I would do the stupidest thing, which is x plus 0, this would work, right? Like, would the compiler understand me now? If I just said that. Then it says Y is still borrowed. What? Okay, so Y is line iter as I32 plus 0 doesn't work. Interesting. So Y is borrowed here may outlive borrowed value. So how do I approach this then? So we got X and Y. We might want to, like, let's change that into a U size apparently. Hopefully this won't like fuck us over. No, this would fuck us over. So this must be an I size, not a U size. Because this like on the edges we may have like negative indices. Um, so flat map thing is going to line iterate map all of these things. Yeah, so we are iterating over this and we should, I don't know, let's try to clone that then. Then it still says come on. This expression has vector pipes. This expression has ref vec of pipe. This one changed changed item 2, usize vec pipe, ref vec pipe. That's very good. Then we are flat mapping. Then it says that this is usize pipe here. Cannot be built from. Oh, wait. Let's try this one as I size at this point, and then as I size at this point. And we could try to move apparently. So let's try to move things, and then we'll see. Okay, so things compile apparently. I don't know why. But we've got assertions that are incorrect, which is very good. So let's look at them. So let's see the differences. This is firstly, we've got a lot of like warnings. So step is allow that code. Yeah, sure, whatever. Just so parse graph. Wait, what? Yeah, this is incorrect. Okay, so this assertion is now working. Yeah, okay, so we just had like a leftover line. Okay, so our graph parser is working. And we expect things to be okay, and they seem to be okay. So let's continue on with walking the graph then. We do need to do something, which is we need to actually, well, not just pass the graph, but we do need to know like where the start is, and then, so let's just have that here. Yeah, let's just, I'm gonna cheat. Let's just put the start. Yeah, this should still pass. Okay, great. So we've got our start, we've got our graph, we've got our everything. So we could try to, well, walk the graph now then. Let's actually infer the start pipe. So that's going to be our next test. So we've got, well, test function test infer start. That is going to, again, return an anyhow results result of the unit, because this is actually just a small test. And we've got not this thing, but we replace S with this thing. We don't have the next line, which is okay. Then we say let graph parse input blah 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 infer start pipe. And the actual, okay, so our actual is now going to be southeast. So our S pipe, let's actually find it. So we've we've got a graph, we've got our coordinates, which is actually going to be 0, 0. Okay, so first of all, let start be, well, find start. Probably there's a better way to do this. So either find or last, find or first. Yeah. So find start. So we've got our coordinate, and we do know where our coordinate is. Then we could say that the start should be southeast. And does that work? It does. That's amazing. Okay, so we do know to find our start, which means that we could stop when we go to our start thing. So that is nice. What else can we say about this? So test in first start is actually a thing. We know how to find the start, which is also a very nice function. So let's actually, that's going to be find start. That's going to return a coordinate. It might be an optional coordinate because we are unwrapping. So instead of that, let's call that an optional ref chord. And that is going to be, well, can we question mark this? Is there like a way to look at that? So we've got the find thing, and then that is an option. Let's try to test it, and it says that expected I size, but found an option. Wait, what? So this one is can only be used on results, not options. Is there like a shorthand for doing this stripping down for results? So let's think. First of all, yeah, expect unable to find start. That's a very good way to strip that in this case. But Rust question mark for option. So the question mark thing is to be very nice. I would like to like unwrap it in a nicer way. This also, I mean, yeah, like it's okay or anyhow unable to find start. Okay, so this is actually a better way to do this, probably. Right? Is that the way? And then we've got that. Let's actually run that test. And the test is passing. Okay, very good. So this one is actually returning everything. By the way, we could say r and then just r.1, r.0. No, that's actually uglier. Yeah, this one's nicer. And find start is not a test function. It's actually a useful function. So let's just put it somewhat. So we now are able to walk the graph. We know how to find the starts. So that means we do know how to start doing things. So let's try and attempt to do something about that. By the way, what are we? Yeah, it's unhappy of unused imports. unused import. Yeah, a lot of unused imports. That's okay. And we've got unused variable expected. Interesting. That's actually, oh, that's not good. So this assertion is actually important. Let's run this test again, just to be sure that everything's passing okay. Okay, so that was important to find unused variable input. That's okay because we haven't done any things yet. Okay, and function part one. Going to accept well, a graph already, a reference to it actually, and all we know is that we know where to find the start. That's not going to be an unwrap, but this is going to be, well, an anyhow result usize, and this is okay or unable to find start. Then we could say start pipe is this thing. And we could go either left or right. So let's walk this graph then. So we've got a loop, which is, well, let mute current start clone, and so we do have a step. So we do need to figure out where to like step firstly, and with the starting. Oh, what I thought I would want to do is actually replace this graph with like okay, so I wanted to basically say let graph be clone, and that's going to be a mutable graph because I'd want to replace one thing, which is let not the visit, no, sorry, graph was the start. So we do know where the start is. We do want let start pipe be infer start pipe, and then graph get mutable start replace with start pipe. That's going to be a borrow. No, that's going to be a clone into that. Or do we need to do something like could we replace that? Oh, we could literally say actually at the start is going to be the start pipe. And that's going to be replaced with insert. And it says that convert to coordinate y. Yeah, using this. And that's a ref, and that's not going to compile. If I recall correctly, this is the things that exactly won't compile. Yeah, mutable borrow occurs here, and then so that's going to be our, well, find start graph. This should be a clone. Then to borrow that, we could say that. Then it says cannot be dereferenced. Yeah, we don't need to dereference that anymore. Then we could continue on with our lives. So this hash map now, like the reason for the cloning is basically so we know our start position, but we don't need to do anything fancy about it at this point. So now we could treat this start position as any other position. So what we want to do in this loop now, we've got our current. It does need to be mutable. So we would want to count the number of steps that we took in order to reach the furthest point. So how would we do that? We could walk until we see the start again, and then divide that by 2, and that would be either the answer or the answer divided by like plus minus 1, or we could walk from both directions. So first of all, let's actually just get the next, like the start directions. So directions going to be that directions going to be step on the graph. Start. Wait, what? Previous current. So not steps. That's next coordinates. Sorry. So next coordinates going to be just the start and the pipe. Okay, so we've got this thing, and it's definitely going to be okay because we have just used that stuff. We know that we have inserted the thing to our map. So we've got two directions to walk from. So how are we going to do this? We've got our mutable current position, and we need to basically do the same loop twice, just by starting with like one direction differently, and then everything should do the same. So let's just define our walk. So function walk going to receive a graph reference, and then we've got start coordinate and the previous one. So start code. Oh, okay. Ref coordinate, and we've got well, not end, but our like first step basically. Also a reference, and that's going to return the length. That's going to be a U size. And then all we need to know is basically, okay, so we've got our start and the current, the previous one is this thing. Yeah, that's actually correct. And steps equals 0. Then we say steps plus 1. Next is going to be, why is it expected code found this thing? No, all of these should be references because, well, and then it says we need to dereference that for a minute. Yeah. That's giving us back an optional coordinate. That's not dead code anymore, so we don't need to allow dead code for at this point. And then we step through the graph once, and that is giving us the next coordinate. And we stop when we see the start. So match next none break. But also we do want to match on the start. So if the next thing if next equals start, then break. Otherwise, we continue our stepping through. And this one is also a borrow. So we are walking everything, and we just need to plus this. Is there a better way to do things? Probably not, but we could try. Okay, so we should have two walks basically. Doesn't really matter. So we could literally just say, actually, yeah, we don't need to. Let's just return the. Okay, so we've got first, second. Oh, so let's walk this one, and also let's walk the other way around. And it's not going to be the minimum. It's going to be the, what is it going to be? Let's add them together, divide by 2. That's going to also, interesting. So this is going to be exactly the same number because we've walked through both directions. So there's no need to do any direction. We just need to return first div 2. And this is going to be an OK plus div 2. So I think this is test part 1, should maybe work. So let's run that through our thing, which is to say let graph the parse graph in 1. Then part 1 solution. Part 2 solution is, well, a to do, but we are not going to let yeah, so this is just a to do for now, and we should return and okay, part 1, part 2. So let's test part 1. Then it says must have a lifetime of static. What does escape what? Say what now? I see. So this is now always the place where basically we should say something like okay or fail to pass. Sure. Then we've got panicked error. Unwrap on error, first value. Let's see where the unwrap happened. So we've got unable to find start. Say what now? On which input? Oh shit. Let's block that back. So we've got our stack trace. This is the second one. So no, that's the first one. So test part 1, we are running this on the input. We expect 4, and we unwrapped. Which unwrapping happened? So let's run this again. So we've got pass graph on this thing, and it claims that it failed to pass. Means that we need to figure out what went wrong. LJS. Okay, so firstly we need to make sure we have support for all of these letters. So we've got F7 pipe, vertical pipe. Yeah, this is basically a sanity check. Oh, there's no S in at least one of the examples. That's okay. Ah, I see. Thank you. Thank you very much. That is correct. And without start, we are not going to be able to find the start. Okay, and now we've got a different number, but that's very good. Thank you, Ran. I appreciate that. Yeah, we definitely we must have, like in the actual end-to-end thing, we must have starts. So we've got our run thing, was the part 1 thing. So how would we know what the number is actually? Let's look at that. We've got, so, oh, not the next, but the current is stop. Then we need to break. And that should pass now. Okay, so part now passes for both examples. I'm not sure how it will handle uneven numbers, basically. But actually, when we're dividing by 2, we are guaranteed to, like when we are running the full circle, we are guaranteed, even if the number is exactly is uneven, the round trip should be exactly 2, because we're doing this visit twice, right? I think so. Let's just assume this works. Let's copy in the actual input from the thing here. So get your puzzle input. We copy that. We paste it into our, well, new file, d10 txt. Paste it in. Then we've got this thing where we just edit this d10 line run. And we've got some number 606 1,800 steps. And we submit that. And we've got a gold star. That's very nice. Okay, so we continue on to part 2. And then we quickly reach to the farthest point in the loop, but the animal never emerges. Maybe its nest is within the area enclosed by the loop. To determine whether it's even worth taking the time to search for such a nest, you should calculate how many tiles are contained within the loop. Ooh. Interesting. So, let's look at that. So the above encloses merely 4 tiles. Yes, that is correct. Only these 4. So yeah, the 2 pairs. These are not in the loop. Yeah, that is correct because they are outside of this well, enclosed loop basically. But what? Oh, but these one are also are not considered to be enclosed. That's okay. So in both examples above, 4 tiles are enclosed. So here's a larger examples, and we've got very small things that are in the loop. Yeah. So how would we filter these out? Interesting. Any tile that isn't part of the main loop can count as being enclosed by the loop. Wait, what? Any tile that isn't part of the main loop can count as being enclosed by the loop. Here's another example with many bits of junk pipes lying around that aren't connected to the main loop at all. Just here are just the tiles that are enclosed in loop marked with I. So in this example, 10 tiles are enclosed in the loop. Interesting. So how would we do that? We've got like a very long loop. We have it in a hash map, but we are able to probe it like linearly because we do have all the coordinates of all the squares of the full square. How would we know if a pipe is within the loop or not? So first of all, we can keep track of like all of the actual numbers. So that's quite easy. Let's actually try to write part 2 now. So what would we need? We could walk the graph and actually do something with the graph. So let's actually define this walk a little bit differently, which is we've got some kind of function, and that's going to be f, and that's do f like so, and this is going to be where f is some function that accepts something and returns something. So oh wait, did I do that in the wrong place? So that's going to be a function where, yeah, okay. So this is, okay, so we've got some function that we can apply on each step. And the reason I want to do that is basically because we've already got the walking algorithm and we just want to change the counting thing to something else. So how would we do that? We do have this, so we've got our function, our graph, our coordinates, so we've got everything that we need here. And this one is actually going to return, well, this is just a unit thing. So we can, we just, basically a callable. And then we could call f on, well, where should we call it? On this step, basically. So we just say f function call, pass in everything. We don't need the steps anymore. then we should go with walk here, and then this is a closure that accepts a lot of things, and then it only mutates the count. So we say let mute steps equals this thing, and oh, walk doesn't do anything fancy now. Walk is just a unit function as well. You don't return steps. There are no steps. And then we say, well, steps plus equals 1, and then we just need to say, yeah, let this is underscore steps divided by 2. Is that possible to, let's just test part 1 now, and it says that set this function to be function mute instead of fn. Ooh. So in this walk, we should say function mute, and it says mute f. So let's okay, so part 1 is still working, and now we've got like a way to basically apply the same function, but we are doing different computations in this function now. So this is a very nice way to basically handle everything else. So this is going to be common because we are not going to do anything differently here. So this is actually the setup thing that's actually happening, well, in this area. So part 1 is now going to be, let's look at that. So part 1 is just going to be the, well, it's going to accept the graph which already has a start thing, and damn. I just wanted to do some code reuse. So yeah, that's going to be just start coordinates and direction. That's going to be and direction is going to be, well, a coordinate pair, so coord and coordinate. And that's also going to be a borrow, I think. And our graph is also going to be a borrow. Now, why is that unhappy? It says found graph thing, and we don't want that. Expected graph. Oh, no. No. This should be a graph borrow always. And that is going to basically, yeah, be this thing. So this is part 1. And it says that, oh, we need to pass in more things. Start direction. Yeah, okay, great. So we've got our graph. Now that I know that we are not going to do anything fancy, we could say literally mutable graph on the first one. We don't need to copy anything. Let's run the test and just make sure that everything compiles and everything still runs. So we've got still like sanity checks. Yeah, okay. Now we could start doing the part 2 thing, which is basically going to accept the same thing, which is the graph start and the graph start location, start direction. And we need to do more stuff within it. So function part 2. So first of all, same arguments. So we could copy that, paste it right here. And then we could do more stuff. So we should say, we should have a hash set of, oh, sorry, visited. That's going to be a, oh, let's call that actually let type loop is going to be the hash set of coordinates that we visited. And that's going to be the, yeah, let's just have that mutable, and we could let underscore equal walk. Definitely not enough. Okay, yeah. So all we want to do is we don't care about the graph, we don't care about the thing, we just care about the current, right? So which one is the current? The current one is the last one. So we've got the current, and we just say pipe loop insert current clone. Okay, so we've got our loop. Okay, first of all, I really like the fact that we could just now walk the graph and just have like a mutable function here that does like magic. That's really nice. How would we approach the whole visited thing? So if we look at the terrible thing that we've got here, where's the S? We've got one slot. So this one is actually, yeah, that's the loop. It's very long, which means that it might engulf a lot of things, but we don't know because it's really hard to actually see through this thing. So we should basically, well, how can we ask if this is within or outside of the loop? Let's think about that. Because this is obviously like the example where we cannot like just say this is the canonical example of this has a bounding, like it has like a bounding box, but we've got things that are outside of the loop basically still. We cannot like just have like a convex polygon basically. Not convex, but like an enclosed body. So let's think about that. We need to think about like this is like an interesting thing because we do have like a lot of like how would we claim something is within or without the thing? We could literally try to walk from each. Interesting, but that's still like yeah, we cannot try to like escape basically. Okay, so first of all, we do know like to color the outside of the graph. That's very easy. So basically everything that's outside of like any coordinates, like its coordinates are bigger, we could like create the bounding box outside the graph. And then we should be able to basically try to, okay, so let's try to like look at that. So we've got some like kind of enclosed loop thing, like that. Here we've got like an island of things that are within, and here we've got an island of things that are within. And here we know all of that is outside. That's quite easy because we can get to the edges of the map from like this thing. So we could basically have like a hash set of all the things that we know that are outside, because we could walk linearly, like we could find the path from their coordinate to the edge. And we can memorize that. And that means that for every item that's within, that can be, we can walk from, we could color in all of that and also all of this, but we could not color. So, oh shit. The only thing that we cannot color is this thing. So we do have this problem where we've got this thing. Yeah, so let's delete this one and this one. So how would we approach the fact that we've got this zero length gap here? Let's think about that. So we've got this one and also this one. So firstly, these are easily colorable. We just walk linearly until we hit an edge. That's very good, very nice. And then we've got like a hash set of all these nodes. What we can do, oh, that's interesting. We can multiply everything by 2. What would that give us? It would make all of these things have a gap of at least 1. Like there wouldn't be there wouldn't we just basically add an empty space and fill it up with ground. Would that work? I think so. I think that would actually work. But that would also create discontinuities and the discontinuities in the loop. Interesting. Wait, but it's possible to be disconnected from the edge and still be outside the loop, right? What? Possible to be disconnected from the edge and still be outside. Yeah, that's the problem. We've got basically the like the problematic area is this one. This area is we need to find a way to like color it in as not outside the loop. So let's think about that. Oh, another interesting way to approach this. I think, oh, that might be even more interesting. So, just like walking a maze, we do. Okay, so we've got basically given an edge of the loop. One edge is definitely outside. One edge is definitely inside. So if we know which edge is inside and which edge is outside, all we need to say is, are we on the right side or the left side of the loop? That's it. And that is very easily determined just by the start position, because the start position, we already know which shape is it. If we are on this shape, oh, that's not true. Wait, let's think about that. So yeah, we need to determine which side is the inside and which side is the outside, and then we can basically know everything about the loop that we need to know. Because we could flood fill and and that is very easily achieved by basically trying to walk from let's think about that. We want to walk from the edge outside. If we hit the edge of the wall, then we know which direction. We just need to we need to find basically we need a bit basically to say which side of the loop is the outside, which one is the inside, and then we could basically walk from each of these edges and just basically delete out all of the things. Yeah, we want to flood fill, but also go, by the way, like YouTube's thing is very annoying, and like the latest message is always hidden by an icon here. Let's just, I'm gonna do like very stupid things here, which is, oh, God damn it. So we've got this one, sorry. Okay, you want to flood fill, but also go in between the adjacent walls. So what I'm saying is that once we've got like the idea of like what's the inside or outside of the loop, like in terms of like given any point on the loop, we could basically walk either right or left from that. Not like given an edge, we should always know. Sorry, given, let's just clean that up a little bit. So we've got our loop, which is basically some blob. So once we figure out the what's the inside and outside of the loop, all we need to do is basically say we just need to go linearly on each edge and just ask like flood fill everything out, and that would also work here on these like enclosed areas. Even if this was like completely shut down like that, shut off like that, like so, we could when we would walk the loop, we would still be able to ask, like we could clear out these edges. And basically, once we've finished that, and we've got our small volumes of things that are actually enclosed with in the loop, like these volumes would still like be intact. We cannot touch them. So yeah, this would, I think, just like sort of work, but we do need to figure out which one is in, which one is out. So yeah, let's figure out if we've got like a better, like we might have just like a flood fill algorithm basically. So flood fill. Uh, this seems like a very good animation, which I quite like. So four-way flood fill using a stack for storage, and this is a queue for storage. Interesting. So stack-based recursive implementation of flood fill. If the node is not inside, return. So yeah, basically that's the thing. So we want to flood fill from the. We need to somehow like flood fill and just. We actually can just do two flood fills, and just the one that hits the edges, we know that's the outside basically. And then we know that the other flood fill is just the insides, and we've got like the islands in between, which we don't care about because we don't count them up in the actual internal flood fill. So that might be actually the way to do that. Just because we don't want to like think about that. The loop can go all around the edges though. Yeah, I mean it could, but it's not actually the case. It could not okay, yeah, there you go. It's not all around the edges. Basically, if we zoom in, we see that it's not all around the edges. I'm taking like shortcuts basically, because we can assume a lot of shortcuts anyway. Anyways, so we've got our loop. We know our start coordinate. We know our like walking directions. And we could now flood fill. So we could say we should have two flood fills basically. Yeah, we can try to make our lives easier, but basically we don't need to find like the most generic solution. So how would we flood fill? We could we've got our pipe loop. By the way, we might want to have it in a vector just because it's we'd like for that to be directional. Let's think about that, because we maybe want to walk that like very fast and in order. This is where like Python's ordered set, like the fact that sets are ordered is very nice, because as long as we insert like only unique items, then everything is like the iteration order is like guaranteed anyway. But yeah, let's just let's have a vector. So vec new, and that's going to be just push. So we've got this one, which is very useful. And now that we've got our pipe loop, I like it that what they do is like pass the ownership as a non-mutable thing. No mutations from this point onwards. Like I love that Copilot did that. So how do we do that? We want to flood fill basically. So let's look at the flood fill algorithm. Let's just we've got 3 parameters: start node, target color, and the replacement color. So we could start with, let's think about that. Perform one step from, wait, let's, so this one is interesting. Like we could literally, okay, so we could like do this from the outside, because like we want to like somehow walk from the edges. Let me think about that. Um, So how would we do that? Basically, we just need like a random node to start with. We could make our lives easier. Let's just go for part 2. And we could say, first of all, so we do want we want a vector? I'm still like, okay, never mind. I'm wasting time on the wrong things. Let's just have a hash set, and if we need to actually walk this, then we do that. So we've got insert. Yeah, never mind. Okay, we've got our hash set of things. Let's just start with any kind of like outside is going to be let outside be of type coordinates, basically 0, 0. And yeah, Sumi assert pipe loop contains outside false. And this one is, yeah, we're still not done. So now we can actually start flood filling. So let's flood fill. Flood fill pipe loop outside. And this should give us the let outside nodes be this thing. Let's create a flood fill function. So fn flood fill. We've got our graph, we've got our pipe loop, which is the hash set. This hash set of coordinates. And we do want like the start point, basically, which is just a coordinate. We could algorithmically, of course, select any start point, but whatever, like doesn't really matter. And this one should return a hash set of all coordinates outside. Yeah. So basically, let mute visited the hash set new. Then do we need a queue for that? So I'm not sure if this is actually correct. Let's there is no vector queue. How would we want to do that? Basically, we would want to say, well, we just want to say loop Sorry. Let mute current be start clone. A lot of crap. Oh my god, so much crap. We've got our loop. And then we say, first of all, visited insert thing. Yeah, that's okay. Visited insert. This thing. And then we should say, oh, so we do want to, a queue just to like add all the other things to visit. So yeah, let mute. Do we have a queue? Is there a thing? Yeah. Oh, so there is a vector double-ended queue. Okay. So we could say, well, we just want to push back, not current, but all of the things that are not visited. Basically. Actually, we are going to pop. Okay, so first of okay, so vector queue from iter start clone. Okay, that's very good. Then we just say let current be unwrap pop. Why unwrap? Why do this thing? And then that has to be an anyhow result of hash set. That's okay. I'm okay with that. And this one is the reference apparently. So we've got our coordinate. We want firstly we want like the south, north. Yeah, so we've got all of these, and basically you want on each of these, if it's not visited, we want to add that to the queue. So oh, but actually, you know what? We could interesting. So we could add like a stop condition where the queue finishes, which might be a good thing to like know how to break out of the loop correctly. But for each of these directions, we would want to add them to the queue. Let's actually perform flood fill one more step to the south. Set the node. So first of all, so actually, instead of like doing this the wrong thing, okay, so we could literally do that in another way, which is to say we are going to push everything to the thing, but yeah, if current, oh sorry, if visited contains current continue, otherwise visited insert. Yeah, that's very good. So that way we've got like all of our visited things, and now we all we need to say is basically yeah, queue extend with extend, that's a very nice thing. So we can just say vec of yeah, all of these. Okay, so now we are flood filling, I think. Is that flood filling? Let's actually do that. And the only thing that we need to say also is we also need to say if this current thing is if the pipe loop contains it, then we know that we should contains it. We should just continue. And it's not in the visited thing. We just don't use it. How do we intersect these sets? Just to be sure that basically we don't like loop over, always like looping around this edge. Hmm. So we've got, we are adding all of these candidates. And then if this candidate is, so yeah, we basically, okay, so this one should be like the, let's call that out of loop. And I think this one is okay. Let's think about that. So this one makes sure that we are basically, okay, so we are visiting in like a random spot in the grid. Not random, but I mean, we are walking and we are just doing this in any kind of order. We will reach a point that is on the pipe loop because we've reached the edge. We are just going to skip that loop, skip that thing, but we already popped it, so that's okay. And we finish when we are done. That's not okay. Yeah, that's not the thing. So we should say, we should pop this basically, and then let some basically if let non-current break. Yeah. So that should be actually, yeah, could literally just match that. So let's just match Q pop and no, that's not possible because it's different return types. Oh, but I don't like that. So yeah, that's going to be, well, current is, it's now an optional thing, but we want to do something like if current is non-break, let current be current and wrap, whatever. And now it's angry at me because it says type mismatch. This should, oh, we are not returning anything. Yeah, so we should return out of loop. Is that flood filling correctly? Well, one way to find out, let's flood fill a graph. We are not asking anything about the graph, which is interesting. That's not good. We should always test if it's on the graph because we should also like avoid the boundaries. So just like we've got this one, we are popping the Q. We are saying if the pipe loop contains it, but also we should say if graph contains key current false, then we should continue. We are not moving onwards with this one. Yeah. This is also, yeah. Okay, so now we've got our edge condition and another edge condition, which is basically we're trying to like flood fill everything. And that way we've got the out of loop thing. So that's our flood fill, that's our outside nodes. Let's try to unit test that. And then that would still not teach us a lot, but basically, oh, it would teach us because we could now flood fill from any random point on the loop. And then if it's on the outside loop, then we know, oh, that's still not good enough. Interesting. Oh, we still need to know like the direction of the graph basically on each point. So yeah, we'll do that in a minute. So let's just unit test that. So where are we? We could duplicate that function, test flood fill. This is going to return an anyhow result of unit, and we've got our flood fill, and yeah, let input be a very small graph. So let's just, do we have like a nice graph? Okay, that's actually a very nice graph to start with. So a very, very nice graph to start with. So we got let input be this thing. And there is no start. We just want to flood fill. So let's flood fill on that's our graph. So we can borrow this graph, and we do need to say, yeah, there is no loop, and we start at 0, 0. And we should, at this point, yeah, we should assert that, oh, sorry, let flood be this thing, and we should assert that, well, flood length is 5. Yeah, I think that's a very good thing, but we should probably also could assert that flood is equal to hash set from ita vec of, yeah, all of this. And why is it unhappy? Because we should return okay. And oh, sorry, to do. Okay, so our simple flood fill test is not bad. Let's try now to up the stakes a little bit. So we've got our thing. Let's do this again, but let's now change the graph. So we've got this thing. Let's just have the start. And we've got another ... So this should now, let's just assume that this is okay by saying, okay, we could say from ita. Okay, so it obviously doesn't understand anything. Do we want to use like a logger thing? Probably not. I mean, I don't want to like do this. Okay, so let's just do that for a minute. Just so we'll have, so we've got start, we've got 7, we've got L, and then here that's J. I think that's like the shortest loop that we could like validly check, and like it would not be too horrible to test. And this one is now coding back into \n, then this one \n, this one. Okay, so we should expect a lot of things from this small thing. Okay, so first of all, let loop be, not loop, pipe loop. Loop is a keyword. That's going to be, no, why are you so stupid? Yeah, that's going to be, well, 2, 0, and then 3, 0, then 2, 1, 3, 1. Okay, so we've got our pipe loop, and we could pass it in. So pipe loop. And we could take a shortcut and just say that we could like take the set intersection of pipe keys and do that, because we have like a contiguous block outside. But let's actually write it manually. So we've got 1, 0, 1, 2, 0, 3, 0. Well, no, it's just incorrect. Um, Copilot, you're making me tired. Yeah, so that's going to be 1, 0. Oh, sorry. 1, 0. And then we've got 4, 0. That is correct. Then we've got 0, 1, 1, 1, 4, 1. Then we should have 0, 3. Then we close it off, say this thing, and that's our hash set. And we should test it out again, and this should fail or should pass. Let's see. Oh my god, it passes. Okay, so our flood fill is somehow working. I'm not sure how, but apparently I can write some code and it sometimes it does not fail. So now that we've got that, we want to determine the direction of the loop. So how do we determine the direction of the loop? We go to the start. Not to the start. We just walk the loop until we find any place on the loop that we know touches the outside. So where are we in part 2? Not walk, but this one. Yeah. So we've got our outside things. And we should say something like it's either, so the direction must be either left or right. And what I mean by left or right is that for each pair, or like for each node, we should know like whether we want to test the left of it or the right of it. And it's always the same one. But like directionality means that we've got an arrow, which means that for each, yeah, okay, so this is now we should have like basically we have we could assume that we walk in exactly one direction, which would make our life easier. Let's try to. So we've got this one. How do we know where should we test? For each of these, we've got like a lot of like for each pair of coordinates and each pair of pipes, we've got like a different direction to test. Is there like a shortcut for that? Let's think about that. I mean, yeah, we should basically be able to test out each pair of pipes should give us one direction. So let's look at that. Where's our like crazy thing? So let's try to, yeah, first of all, yeah, next, not next, but let's call that just left of pipe, left of pipe. And how would we know that? So left of pipe is going to accept 2 coordinates, which is the current and previous ones. So yeah, that's going to be our current coordinate and previous one. And it is going to, we would have to, and also the graph, because we have to know like where we stand. And that is going to be like, yeah, the left of the pipe, just left because we can arbitrarily choose like one iteration direction, doesn't really matter. And then we do need let pipe be this one. Okay, so that's going to be, well, current pipe and previous pipe. So yeah, first of all, we could now match on that. So let's match on this pair. So we've got current and previous, or let's actually flip them around because it might be useful, more useful. So we've got some. Oh, we actually don't care about the coordinates, do we? Because we do, if we know the current. Okay, so that might be nicer. So left of pipe could also just work without actually doing like this whole optional crap. We've got current pipe and previous pipe. And then we don't have options anymore. We just go with match on both. So current, previous and current. Current. Okay, so this should be a lot of pairs, but some of them are invalid, which means that it should be not too crazy to think about all of that. So, oh, that's actually not good enough because this one is just, for example, north-south and north-south. This one is, well, what's the left of that? We don't know where we came from. We don't know where we are heading. So we must have the coordinates, not just the thing. So, too bad. We do need the graph. We've got previous coordinate, current coordinate. So we've got let xy. We've got the previous xy. And we do want oh, dx dy is actually a nice thing. Interesting. Oh, it's actually like the left of the pipe is actually more than one thing. It's actually like two candidates. Like for a right angle, it's actually two candidates. So and nothing else. Interesting. So, interesting. Hmm. How do we know to know this? Interesting. I'm not sure. Like I'm kind of stuck. Let me think about that. We could actually maybe try to walk this and do something else. And then like keep like some kind of state, and that could maybe work. So let's just go back to part 2 and start walking. By the way, part 2 on the graph. Yeah. So now that we've got that, we've got our outside nodes, let's actually try to walk and do something, which is we just pass this one in. And then we've got more things to say, and we just want to walk the same direction every time. Yeah, that's good enough. And we've got our previous coordinates, and we don't need the graph right now. So Um, how can we run? Like I'm kind of lost on this one. So we are walking. We know where we are. We know where we are headed. By the way, this walk thing. Start first. Okay, that's okay. So this one is when we are start. Yeah, this is not. This is basically definitely incorrect what Copilot is now offering, but sure. Um, let mute loop direction is going to be well, it needs to be something. I don't know what it is. Let's just call that a boolean of like left or right, basically. And we don't know yet our direction, so it should be an optional bool. So that's going to be an option. It's going to be none. It's going to be an option of bool. And let's actually, okay, so we should have like an enum for that. Like there's no need to be savages. Loop direction. That's going to be either clockwise or counterclockwise, basically. And that is going to derive a lot of crap because we always need to derive a lot of crap. Then where we are, we've got our loop direction, which starts with none. We don't know our loop direction yet. We always take like one direction, which is that's okay. Like we always start like left or whatever this direction is. We walk on the loop, and then we should say the current node. We should look at it. It's actually a coordinate. So let type the graph get current. And then do we want to do something about that? Is that possible to? Yeah, it's not possible to actually question mark this. So, but this is actually interesting. So it's okay or anyhow error. Unable to find pipe. And that is going to fail to compile, of course, because this function is not supported, does not support actually returning anything. So let's maybe do that. Anyhow, error. And then we should say, yeah, should unwrap that. Okay. Then our walks are now not going to work because we should say okay on this. Yeah. And also here we should say okay on the scrap. Oh, found bool, I see. And then we are here and we can say pipe or wrap with okay. Oh, yeah. First of all, yeah, just okay here. Okay, so we've got our pipe, which is we should be able to find this pipe because it comes from the graph. should also get no, not next. So we've got our previous pipe, this pipe, graph get, whatever. And we want to match on the loop direction. So first of all, if it's none, we need to try to figure it out. So that's going to be one thing. So we need to infer the loop direction, which we don't know yet. So this is our to do. Then we've got, if it's clockwise, then we've got a to do. And if it's counterclockwise, then we've got a third to do. So all of these should be something. Let's actually have this OK unit here because we will need it in a minute. So firstly, this should be was the loop direction. So this one should be mutated if we could help ourselves. But that might not be the case. We might not be able to infer that. And then if we know our direction, then what we need to do is basically we need to flood fill from this area. Like once we know the direction, we need to flood fill everything. Oh, we don't need to do that. We need to just infer the loop direction once. Then we could break. Then once we've got our direction, we could literally walk and like do the other things. So okay, so we just we're just able to do this once we've got our loop direction, then we can just do nothing. So basically everything else is just nothing. Yeah. Okay, so let's infer our loop direction. Infer loop direction. And that would need a lot of graph because we'd need to first of all see the outside node. Okay, so what else do we need? We need our coordinates, we need our graph. Okay, so a lot of stuff. Graph. Actually, you know what? That's as good as places I need to actually do the calculations. So we've got yeah, Copilot is offering shit. That's not good. So we can match on something. And what do we want to match on? So we want to match on our current pipe. And okay, so are we traveling, first of all, are we traveling basically south or north, or like what is the direction of travel? We just need an arrow. So how would we know this arrow? We could try and wait for like a good position. So what would be like a good thing to watch for? Basically, two corners is really easy, or basically a corner and anything is really easy. Unlike straight and straight, which is hard or like ambiguous, and we cannot infer anything out of that. I mean, we could because we could look at the coordinates, but basically, okay, so we just need to. Okay, so first of all, we need to figure out like what direction are we traveling in, and then we need to ask if any of the external nodes are within the outside nodes. So this is the two steps that we need to find. So direction of travel is something, and then the next thing is looking at the outsides. How do we do that? So direction of travel is always like southeast, northwest, like the edge in the graph. So it's either southeast, north, or west. So let's do that firstly. So we could match on the coordinates themselves, not on the pair of coordinates. or the actually we could match on the we could do arithmetic between them. So that direction of travel is going to be current minus rev. Oh my god, this is that's the thing. I think we just need to deref both. And then it's going to say that it's not implemented. Cannot subtract isize from isize. So let's derive that maybe bit better. Or you know what? Yeah, basically this. Now we can match on the direction of travel. Hmm. So if it's 0, 1, that's going to be something, and that is going to be let's think about that. So let's actually let's give that names. I think that would be nicer. So we've got direction. Yeah, sure. Northeast, southwest. So let's just track that into a function, or you know what? Simple. Direction, new, fn, new. I think that is nice. That is nicer. Oh, no, wait. Yeah, that's okay, but you know what? That's actually, yeah, good enough, I think. So let's just use this now, because we can. So where's our part 2 thing? We can say direction, new, this thing. And now we can match on these easily. So if we're traveling north, direction north. And so and we can now look to our left and to our right and figure out if one of them is maybe on the outside. Sorry about that. So we are traveling north, and we want to take into account our pipes. So we should look not only on the pipe, but we should look on, like, for each pipe we should give options of what to check. So each pipe could actually give that options by itself. So we could import pipe fn, not is start, but left and right. That is going to return two very small vectors of coordinates to check. So that's going to be not coordinates. Well, I mean, it is going to be a pair of coordinates. Let's think about that. Yeah, so we would want something like, yeah, a tuple of two vectors, and each one is going to be a coordinate and a coordinate. Let's just call that xy. Type xy. That's going to be a tuple of coordinates. A vec of xy and another vec of xy. And that is going to be, oh, that's going to take a reference to self Um, okay, let's just look at whether Copilot has completely bullshitted us or not. So first of all, north-south is actually going to, this is going to be a very big list of things, right? This is going to be, actually, it might be a set, not a vector, but let's give it a go. So this type of self does not need to be arbitrary. What? Consider naming this parameter. Oh, okay. Apparently we could do that. Okay, so northwest, that's going to be north-south, that's going to be -1, -1. Oh, sorry. Yeah, okay. Basically, we look at ourselves in the center as if we're 0, 0. Then we need -1, 0, and then one more, which is, come on, so stupid. And then it should be -1. Wait, what? What's going on here? -1, 0. And then, I'm sorry. Wow. Expected chord found I32. Why is that? I size. This is a vector of tuples, right? So first of all, yeah, let's just remove all of this crap, which apparently, okay, so we've got okay, this one is to the left, whatever that means. So we've got -1, -1. That's like left and up. And then we've got -1 like so. Then we've got -1, 1. That's left and down. And that should be a thing. And why is that saying that this is not good? Because it shouldn't be, oh, sorry. So a coordinate is already x and y. So we don't need to do anything. It's not a pair of coordinates. It's just a coordinate. So this is a vector of coordinates. That's going to be another vector of coordinates. Okay, so we've got that. Then we say the next thing. Yeah, okay. So this is like our left and right for each pipe. East-west is now going to be -1, +1. That's okay. So northeast is actually, let's think about that. That's actually interesting. So we are going north and east, so that gives us like a very big L of things on one side and just one coordinate on the other. Oh, that's actually not even correct. We've got, yeah, okay, so yeah, a big L and nothing, and on the other one just one coordinate. So on the left of northeast, we should have a bigger thing, which is, let's call it -1, -1. We've got -1, 0. We've got -1, 1. We've got 0, -1, and 1, -1. Yeah, that is correct. And here we should only have just one thing, which is 1 on x and 0. Where's 1, 1? 1, 1 should have been here. 1, 1. Okay, so 6 in total still. Oh, wait, am I fucked it up? Let's think about that. Something here is wrong. Let's look at northeast as a grid. So we've got our northeast, call that L, and we've got that should be well, left, 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 left. That should be nothing, nothing, right. So -1, +1, +1. Okay, so we should have 3 -1s. One that is 0 offset -1, and then that should be just 1, 1, not -1. Yeah, wow, that's a lot of stuff to write. Northwest. What are the odds that Copilot is not bullshitting? Northwest. Definitely not correct. Yeah, so northwest is now, let's flip that over. So we've got J, and now we've got left, 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 star, right. Oh, sorry, that's actually not correct. That's right. Yeah. So this is now our left. So this one is now the vector. And we should have 6 elements here. So let's see if Copilot is bullshitting or not. Of course it is bullshitting. Why shouldn't it bullshit? So this one is -1, 1, -1, 0, -1. Wait, we are on the Y thing. So we should have 0, 1, and then we should have here -1, 1, no, 1, 1. And then we should have, what is it? +1, 0. And we should have, what is it? 1, -1. Yeah. Southeast. I'm very skeptical of Copilot, but let's just erase all of that. So southeast, let's just duplicate that. So we've got, that's going to be, so southeast is 7. No, not 7. What was southeast? We've had another letter for that. LJS7F. So that's southeast. So southeast is going to be star, star. Then everything else is left, left, left. So now that we've got that, let's type that in. Oh, that's going to be terribly long to type all of that. Okay, so that's going to be -1, -1. 0, -1. Yeah, that is correct. We should have 5. Yeah, 5 things. And then vec of so -1 thing is okay. Oh my god. So much translation tables, so many translation tables. I probably have a better way to do this. These ones, let's actually make sure they are correct. So this should be not 0, -1, 0, -1, 1. And this one should be 1, 1. Yeah, 1, 1. Next up, southwest. So southwest, let's look at southwest. How does that look? So southwest is 7. That is now star. And that is left, and everything else is right. Yeah. So southwest has got -1, 1 as the thing, and then all of these is -1, 1, 0, -1, 1, -1, 1, 0, 1, 1. Yeah. And everything else is unreachable. Oh, that actually is useful. Yeah. Okay, so we've got all of that. And where do we want to use them? So we've got this thing, and we want to, this is the direction of travel, and we do know what is like to our left and what is to our right. So if we are traveling north, and we've got, firstly, we've got like basically left, right, like of course. So that's probably just incorrect. Let's just ignore whatever Copilot is actually doing. So we've got our left and right thing. We are traveling north. We should look if we see to our left or to our right an outside node. That is it. So left theta any outside node and thing. So we could literally break. I mean, it's enough. Let's think about that. We are walking the thing. First of all, okay, so first of all, match on loop direction. If it's some if let some loop direction, then return okay. We don't need to do anything. Otherwise, let's actually do the thing. So if we are traveling north and we could look to our left or right. So we could say just left Oh, so actually we do need to do this anyway, so we could say just this. So left and right, and we could now iterate. So say left theta. So we do know we just have xy. And it says we could say, yeah, not like that, but we should say contains current zero xy, yeah. Okay, so if our outside nodes contain yes, so this is, well, not yet. We just know that left is a thing. So let out on left is left iter any coordinates contains not coordinates but the current plus. So that's going to be a little bit more complex. Current plus chord, yeah, and current.1 plus chord. So seen outside on left side. Then we could do the same on the right. First of all, we can assert that we can assert that not all are true. So we could say that not equal, but assert that not both are true, basically. And that would be not loop detected. Basically, yeah, okay. Invalid, something is invalid, and we don't care about that for now. So now that we've got that covered, this is actually has three states, basically. So it's either left, right, or none. So we're traveling north, and we see it on our left, then we are clockwise. If we see it on our right, then we are counterclockwise. Yeah. Okay. So left, right, none. So we should have like a left, right, none thing. So so much stuff. We've got, let's just call that let yeah, well, this is quite early, but sure, whatever. We do want like a direction, basically. We need another enum, which is turn left, right, whatever. Direction. Not this kind of direction. Outside. Yeah. And that is an optional outside, basically. Part 2. Wow, this is so much code. Hate this. Match on. Okay, so let outside be. That's going to be an option of outside. Match on seen outside on left and seen outside on right. Yeah, now we've got our time for asserting everything that we want, which is to say true, false, left, right, otherwise none. No, that's not true. False, false is none, and this is actually an anyhow. Anyhow. What's the problem? Oh, I see. That needs to be Dale or something, right? Okay, so we've got our outside. We can now match on both things. We can match on our direction of travel and our outside thing. First of all, easily, anything plus none does nothing. Then we've got direction north plus some left. So some direction. Oh, we actually could. Okay, so I see. So we could literally, instead of that, we could just directly unwrap that. And that is going to just be not an option, but this thing. So, okay, so we could match on that, and now we don't have the whole none thing. Oh, but it might be none. Oh, shit. So that's not an unwrapping that we can afford. And that's, yeah, that's an option. Okay, if let equal outside, return okay. We're just not gonna error out for now. Then we could say let outside unwrap. We've got well, outside left, and we know that direction of travel, not direction of travel, but oh my god, loop direction. Name of that. So much stuff. Loop direction is some clockwise. Wait, north, left, counterclockwise. Yeah, right. Why is it unhappy? It says expected anyhow result found direction. Ooh, interesting. So wait, is this direction of travel? We should have unwrapped that. Then it says expected direction of or something found direction. Now should we do this? We should wrap this. Like so? Yeah. Okay. So much pattern matching. Oh shit. So we match on that and then we return and everything's fine. We don't care about the previous pipe apparently because we already know what to do with our direction of travel because we look at our current and previous thing. So we don't need we don't care about like the shape of pipe, only that we got from here to there. So now we have determined either we are clockwise or counterclockwise. Let's actually just look at that. Let's reason about each one. So we've got north and left, that's counterclockwise. We've got north and right, then clockwise. We've got south and left, that's clockwise. South and right, that's counterclockwise. East and left is counter. And then east and right is clockwise. West, left, clockwise. No, that's not correct. West. So west, left. That's counter. Is that true? Wait. So that's east, left, counter. West, left, also counter. North, left, counter. South, left, counter. So that doesn't really matter what was our direction of travel. All we need to know is, no, that's incorrect. What? I'm confused. We are, oh my god, so annoying. So let's actually take this down. So we've got can travel in 4 directions. And we see our outside to our left here. We see our outside to our left. For whatever left means, doesn't really matter at this point. We could have been also this kind of thing, and then we saw our outside to our left. Then we know this loop is actually outside. Doesn't really matter then what was like our previous direction of travel. That's true. Let's think about that if that is actually correct. Let's try to be adversarial to that. So we've got so here we see everything to our left. And also here, we see everything to our left. So we know what our direction of travel is, and we know how to flood fill everything. What happens? What else do we've got as left? So we see this is also left. Okay, so wait, this is interesting. So here we've got the same corner. We see it to our right. So it really does matter whether we came from the if we came from this thing or from this area. Let's look at that. Let's think about that. My brain hurts. So we know where we came from. Okay, so we do want to know whether we are traveling clockwise or counterclockwise. We can tell that just by that. Okay, so if we're traveling up, then plus we see to our right in this case. Then we are traveling counterclockwise. So if this is a southwest corner, so southwest. So it's all about like we are traveling. Doesn't really matter though. Need to see to whether we travel. Okay, so if we are traveling north and our outside is to our right, then we are traveling counterclockwise, right? If we are traveling, wait, this one is the travel direction. Yeah, call that travel direction. So yeah, so if we are traveling north and our outside is to our left, wait, outside, not inside. Ah, okay. If we're traveling north and the outside is to our left, let's look at that. How would that look? We've got a corner like so, and the outside is this area. This is traveling north and the outside is to our left. Doesn't really matter if this is, that would work also if we are in this type of corner, then the outside is to our left. That is the same thing. Is that true though? Because like, let's try to think of like an adversarial example. Let's make that incorrect. Let's try to make that incorrect. So here, if we are traveling this area, we start here, then we are traveling north and the outside is to our left and we are traveling clockwise. That's okay. Then, okay, so the outside is always to our left. Then yeah, basically when we're traveling north, we are traveling clockwise. That's the way. That's the only way that is possible. I think. I should hope. Then if we see the thing to our right, then we know that we are counterclockwise. Then we've got, if we're traveling south, it should be the opposite, right? Because if we look at traveling south, so we've got this travel south, we see, okay, so here we've got the outside to our, well, is not the left in like the, okay, so it's left not when not from the graph frame of reference, not the direction of travel frame of reference. It's from a global view frame of reference. Wow, that's a thing that's hard to say. So if we are traveling left, the outside is to our left when we are traveling south. Here, so this is the outside. We are traveling south. That means that we must be rotating this way, which is counterclockwise. Then the outside is to our right, which means we are rotating clockwise. Then we've got direction of travel east. And this is where like the thing, okay, so this should have been interesting. So this might not be like the outside might be like to the top of us or to the bottom of us, which is not exactly like left and right is just not the right way to look at that. So let's think about that. So this is not exactly, yeah, this is not exactly left and right, but more like top and bottom, basically, when we are looking at that. So just, okay, bad naming. Let's continue. Okay, so when we're talking left is top, right is bottom. Here. So when we are traveling east and to the top of us, we see something that means we are at the outside, then that means this is the direction we're traveling, which is clockwise. When we are traveling east and the right, we see to the right, we are traveling this way. So going to be counter. When we are traveling west and we see something to the top of us, and that's a very good question. What do we mean by top in this case? So let's look at that very soon. So we are traveling and we see to the top of us something, then we are traveling counterclockwise. Wait, no. We see the outside. Yeah, so we are traveling counterclockwise. And if we are traveling west and we see something below us, then we should be rotating this way. So that should be clockwise. Now for the direction of travels east and west, we should just make sure that this left and right thing is like correct, basically. So that should be, well, we should call that not left and right, but top or bottom, but we already, I'm too knee deep in this, so let's just make sure that for things that go like north, east, west, top is always the negative coordinates in the y, and yeah, that's okay. And for corners, it's always the same thing, doesn't really matter, but we cannot, for each corner, there's just left and right correctly. Okay, so I believe this is correct. That was the only problematic one, and I think it's okay. It is okay. But let's think about that. This is only the direction of travel. Doesn't really matter whether we've seen that. Yeah, okay. Seems somehow legit. This is, and I'd be hard pressed to find this correct. This is probably incorrect. Okay, but we do know we have our outside nodes. We have our loop direction at this point. We can assert. We could say let loop direction be okay or unable to determine. Yeah, that's okay. And now that we've got that, oh my god. We could walk again on the loop. This is the third walk. So on this walk, we could do, let's say, first of all, let thing be walk on the same graph and start and something, and just I'm gonna wait. Walk. Yeah, that's the one. So we've got the graph, we've got the previous, and we've got the current. And we need to do something about that. So we've got our loop direction at this point. It's either clockwise. We know it's exactly one thing, which is either clockwise or counterclockwise. And now that means we can flood fill all of the outside nodes. So I think that should work, maybe. Yeah, we could flood fill the outside nodes at this point. So let's try and look at that. So if we are counterclockwise, then we know for each kind of node what we should do. So we've got our current node. We only look at that one. So let pipe be yeah, unable to find pipe, that's okay. And then all we want to say is candidates. Oh, so we could, once we know that, we could basically, okay, so we should have like, oh, we could actually just use, we could literally just have the insides now because we know the direction of travel. So, so let mute inside. Inside is going to be a hash set of coordinates. So we could actually count them up, but because we don't want to do any duplicates, let's actually have that as hash set. So yeah, that's going to be a hash set new. And we've got our loop direction. And all we need to say is how do we do that? We need to add all of them up into this hash set. So that's going to be, we need left and right coordinates. So let let x y wait, let's just do, so we've got pipe, left and right, we just need one of them. So let's match on the direction of travel. Wait, that's not enough, right? Because we need to know where we're heading in order to take the left or right. Because if we're traveling south or traveling west, we do see other things. Interesting. So if we see an outside, we could already put the outside and the inside, like we could also just add nodes to the inside, right? But we don't know because we didn't. We might have a few iterations where we haven't figured out the direction, the direction of travel. So that's not going to work. So we need to walk that again. Okay, so never mind. So good, we've got our direction of travel. Let's just add that here just because we probably would need that. So we've got our direction of travel. We've got our left and right thing. Oh, I see that I already have this key thing, keycaster here, and I haven't used it. So we've got our direction of travel, and we know that we need to either probe left or right depending on our direction of travel. So we've got our left and right thing. So we could match on this thing. So we've got let left, right equal left and right. And we do need to add things to it, but to them, but that's going to be later. So we've got OK thing, just so the ID will shut up. We could match on the direction of travel. So it is so wait, let's call that let called the match on direction of travel, and it might be, yeah, if we're traveling north and we need to match not only on that but also on the loop direction. So we've got loop direction, and now we need to find out. So north and clockwise, north and clockwise we want in right. North and counterclockwise we want our left. South and clockwise we want left. South and counter, we want our right. east. This is all very probably like I could take out a lot short. I could probably take a lot of shortcuts here, but I'm just like really not in the zone. But basically, I'm already invested. We are traveling now east and clockwise. We want the top, which is left. East. Oh, sorry, east and clockwise. So that's actually going to be the bottom. East clockwise, yeah, bottom. That means that east counter is the top. And west clockwise top, west clockwise bottom. Okay, so this is our vector of not coordinates yet, but actually that's just going to be x and y's to add to our current coordinate in order to probe it and make sure that we've got a thing, which means, okay, so inside is going to be extend that, yeah. So extend iter map on, yeah, the current plus all of these. So this is our hash set. So we've got all of our inside candidates. We need to, first of all, assert. This assertion is very important that inside so these perturbations must never be on the outside. So we could assert that right here. So let's just assert that instead before we actually extend these. No, we could assert like in the end, it doesn't really matter. So we should say iter all not pipe loop contains, but all outside nodes not contains this coordinate. Okay, this assertion is very important. That means that like this is a sanity check for our whole algorithm. So we've got our loop direction. We've got our side, all of our outside nodes. We've got all of our inside nodes. That it's not yet all of them, but it's all the candidates that we can flood fill. So let's look at how we actually do the flood fill. First of all, we should filter out. So we should say let inside the inside filter on pipe loop. What? Dot collect. That is going to be a hash set of infer. So yeah, the pipe loop must not. Yeah, we should remove like previous things from the loop. Now we can flood fill that thing. So we should say something in the lines of let's look at how we said flood fill now. So let's change that because it's going to be a hash set of coordinates, and then that means that we could basically iterate over all of these. So start. Oh, interesting. So we don't need to do anything fancy. We just need to say that's going to be a vec of coordinates. And then all we need to say is, well, start clone. That's very awesome because that now means that all we need to do also we need to update our assertions to be a vec of this thing. We probably have another vector somewhere. Flood fill here, yeah. that should be a vec of this thing. And we should have another, yeah, vec of, that's very awesome. So we've collected all of our starting points. We've filtered out all of the loop things. We have asserted that we haven't leaked to the outside. We've got all of our coordinates now that are not the loop itself, basically. And we could now say, let flood fill. So now we're going to flood fill basically all of the spaces. So flood fill is going to accept the graph. It's going to accept the pipe loop. And it's going to be the outside, not the outside, but the inside. And that's going to be not a hash set, but it is going to be a vector. Cool. So yeah, we are filtering on that. So we could say vec of coordinates. And that is going to be a vector of coordinates. And we could actually gather that as a reference. We don't need the thing. So I've got all of these calls. Let thing could pass in a reference. And we could pass in a reference also here. And that is now we've got our flood fill. We should say now let inside nodes. So that's going to be not inside, but yeah, I mean, this is inside starting points. So inside candidates. Oh my God, this is so long. And now all we need to say is return count. And that needs to be okay. Oh, that was terrible. Impaired. We've got this one. Yeah, let's take it as is. Or, you know, let's actually take this one because we know. So let input be this thing. And then we could assert run part 2, not yet, not this one. So this one should be equal to 4. So let's run that and pray for the gods. And it says that this one should return results, returns option. But what? Wait, what? Function, this function should return result. Our option to accept thing. And why is that? The question mark operator cannot be used in a function that returns result or option. Or other type that implements from residual. Wait, what? So this function should have been, yeah, should return either this thing or, so it's, oh, so I see. This one is, yeah, we should say something like call f, and we should match on it, basically. We should say match on f. Isn't that like a nice way to unwrap that? Yeah, error break, but like I want to actually return the error. Um, wait, so if it's okay, then I want like the error E. Uh, I mean, I don't want to unwrap this, but I might do that just because I'm impatient. So if we unwrap this, what would happen? Let's try to compile that, and then we would face another problems. Okay, so oh, that's a reference. That's okay. This one is trait bound, borrow not satisfied. Wait, what? Could be this thing. Okay, that's very good, very well. U dot extend. Then we just, it's not Q. There is no extend. We need to push back. So if this is a vector, vector of coordinates. Oh, might be just this thing. Yeah. Then it says that temporary value, blah, 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 blah. Oh, damn. So clone, did this work? No. So yeah, apparently these references must live somewhere. So that means that this must be a vector of, yeah, so that needs to be a vector, the Q of coordinates, the actual ones. So we need to, from iter, map this thing. Yeah, that's very good. That means this is now going back to this area. We don't need to do any cloning here. This is compiling. And of course, things would obviously crash because that's the whole point. Um, how did this happen? Move to top left, bottom left, bottom. Wait, what? Okay, yeah, back to normal. So unable to determine outside. So this one is not good then. So we've got two trues, two true values, which means that something is fucked. We are matching on left and right. And how come that is happening? It's we say outside node if any outside nodes contains coordinates past this. So let's debug that. PVG. So our current is 1, 2. And this is literally the first one. Oh. Okay. So let's look at the unit test. So we've got 1, 2. Firstly, I'm surprised this one hasn't actually failed, because we've got O's and I's here, and I thought this would actually make things fail. But let's look at that very, like, okay, so X, 1, 2. Um, so seen outside on left, I believe that, and seen outside on right, I don't believe that. Um, hmm. There's no way this one has exited before that, so that's interesting. The first time we're visiting this. Um, Wait a minute. Let's just let's turn all of these into actual pipes, actual ground. Just so we'll have like an actual. I believe this might be like a problem. So I'm just. Okay, so we've got another thing, which is panicking. Interesting. So code char. And that is correct, because we have, I fucked this over. Okay, and we've got another thing. Ooh. So we've got 12. Pum, pum, pum. So let's try to figure out what the fuck happened. So we've got this debug thing. So, oh, we start with S, which is basically the start. Then we see the outside on the left. We don't see the outside on the right, which is correct. Then we don't have enough debug prints to actually know what happened. So this one seems to quit very early, and that's okay. Because, oh, I want to actually like see if it determined correctly the direction of travel. So Now that we've got that, let's actually do this. Loop direction, basically. So let's debug that and say, so we could say dbg loop direction. So our loop direction is counterclockwise. Interesting. But we know if this is correct. Let's look at that. We start here, and this is the start is a southeast corner. So if we look at the southeast corner, so southeast corner, let's look at that. Okay, so southeast, the first one is traveling to the bottom. Interesting. And if we look at that, our next coordinates, if we take that step, like the first step on the walk, always take the first one. Like this is the, okay, so we are traveling counterclockwise. That is correct. So we know that we're walking correctly. And that means that if this is our walk, then we need to look at that more, like we need to look at this better now. We are walking the graph for each one of the nodes. We are finding the direction of travel. We've got our things. How do we formalize that correctly? So let's actually print everything out because we have that. So dbg on xy current. Let's flip them because we can, and probably borrow. And we've got a lot of stuff. Very good. Oh, that's very long. So let's look at that. We've got, first of all, we've got our current, this is like the start position. That's very nice. Then we've got y as should be 3 things, and they are 3, right? Wait, 1, 2. So 0, oh, 2, yeah, because we always start at the start. Like we always skip the start, basically. So that should be now traveling. We should be seeing, yeah, 1, 1. Wait, 1. Wait, what? Why is that? That is incorrect. That is looking to the right and not to the left. Interesting. We are counterclockwise. We are traveling down. We're traveling south. We should have taken the inside. Okay, we are looking for the insides. That's okay. We should not match anything, which is, let's look at that. So inside candidates. So we are extending that. Yeah. So these ones are the inside candidates. But we should filter out any of those that are the starting, like the loop itself, which is okay. So we've got that current. 1, 3. Again, like the same thing. Okay, we are traveling, then we should reach a corner. Where's the corner? 1, 7. 1, 7 seems like the right thing. Let's look at that back. Yeah, so 1, 7 is actually, yeah, should give us this thing. Then we should walk again. We should see 2, 7. That should give us up. So -1, -1, -1. That's very good. Then 3, 7. Also -1, -1, -1. 4, 7 should give us exactly -1, -1, the upper corner. That's very good. 4, 6 should give us -1, -1, -1. That's okay. This is x to our left. Then 4, 5 should give us one corner, which is -1 on x, 1 on thing. That is also correct. 5, 3. 5, 3 should give us 3 bottom values. So that should be, yeah, y on the bottom. That's okay. 2, 5. So 2, 5 is going to be interesting. That's going to be 0 on. Okay. Wait. 0 on x, 1. Okay, that's this one, which is okay. So this is our inclusive edge at this point. So now we are on 2, 4. It give us 3 values, which are on to the left, which is -1 x, -1 thing, 1 is fine. Yeah, that's okay. Current is 2, 3. Again, should be the same 3 values, and then the corner 2, 2. That should be just one value, and it is -1, -1, which is correct. So all of these. Oh, so we should dedupe that. Should we? We probably should. So far, I think we've seen all of the corners. We've seen L's, 7s, J's, and starts, which are F's. Oh, we have, yeah, and also the F here should have worked. So yeah, this is so far so good. Let's actually just let's just continue tracing that. So we are in 2, 2. We are, oh, interesting. So 2, 2 should have been just, oh, it's all of this area. So yeah, that's okay. So -1, 0, -1, yeah. So all of this top row, and then also, aha, this is the bug maybe. Okay, so apparently I've got a bug on. We were traveling north, and we are on a counterclockwise. Okay, so the F has a bug, basically, which is a what is it? Southeast corner. So let's look at left and right. Left and right. Let's look at the southeast thing, and we've got. Is it the southeast corner? So, yeah, southeast. So we should have -1 minus. Okay, so let's just look at that F very closely. So we've got -1 minus. We've got this one. Okay, so let's just do this. Okay, this is definitely just incorrect. So yeah, -1, 0, -1, 1. Then it should be x. Should have been 0, -1, and 1, -1. Okay. Let's rerun that, and let's see what we actually hit. So let's run that again. And we've got maybe a different thing, maybe not, we still don't know. So I want find something like that, and just it's going to be 2 and 2. Okay. So we've got this thing, which is -1 on the x thing, and then it should be x0 -1 on y, because we are on this corner. Let's just compare that back to the thing. Yeah, so we are reasoning through this very, very slowly. So 2, 3, we have moved. Wait, what? 2, 3 is, oh, sorry, 2, 2. Yeah, so then that should be 3, 2. Yeah. So 3, 2 should have all of the top row. We move forward until we see 7, 2. 7, 2 is a corner which is -1 on x. Wait, what? -1 on x, 1 on y. Is that correct? That is incorrect. So interesting. When we are traveling east and we are hitting and we are going counterclockwise. Interesting. So this is actually, in some sense, this is actually going clockwise within this counterclockwise loop, and this is where the bug actually stands. So how do we know? We need, like, the loop direction is actually incorrect here. This is why we're also flood filling this thing. So keeping this like as a clockwise loop is not good enough yet. Let's think about that. Shit. So we could say, okay, so this the flood fill is working, but the algorithm here is still not good enough. Because basically when we are traveling, we should have done something differently instead of like trying to understand where's the clockwise and counterclockwise thing. So um, so this loop is changing direction basically. Crap. So we've got our direction of travel, which is either north, south, east, west. And we already kept track of the loop direction at this point. So we don't need to quit early, basically. We need to iterate, and while we know our loop direction, we need to do something about that. So let's actually not quit early here. And we've got this thing. So now we know what our loop direction is at any point in time. And then we've got our outside somewhere at this point. So if we've got no outside to speak of, then we need not to do anything fancy. And if we look at that, we just need to say we've got our direction of travel. We've got our loop direction. And we can say Okay, so let's just let's move things around. So we've got our candidates. We want them here. We've got our flood filled outside nodes, which is okay. We've got our loop direction, which is just a thing that we can determine at every point, and we need to keep track on like what's the most recent loop direction that we've got. And then for each of the inside candidates, this one is just terribly long, so let's just extract that into a method. Infer loop direction. Okay, so instead of all of that, we could have done that way more nicely. We could have said match on this, like so. Then we just needed to say some counterclockwise. Oh, that's and more extractable as a function. Yeah, and now we can extract that into the loop direction. Okay. So we've got our loop direction, we've got our outside. It might be either on one side or the other, or it might be none. And then if it's none, then there are no things to speak of, basically. So we've got our loop direction. We could memorize that. We could now match on any of these. So we've got our left and right. Let's actually take that now. Where's our left and right things? So inside candidates, we need to extend them with either left or right. X, Y, eta. So let's extract that into direction of travel, loop direction. Let's think about that. Could have said that. That would be nicer. No, actually, we could have done that cleanly, like so. So, yeah. Loop direction, direction of travel, pipe. Yeah, that's very good. Let's say that. And that should be, let's call that nodes to test. Possibly inside. Actually, we could literally just iterate on that directly. So we already know what we're planning to do, which is, yeah, so we could just track that into a variable, which is this one. So we should say this one is the nodes to check. So all of that is to say nodes to check. Now we can transfer that into our next thing here to our previous function is this one. And we should match on loop direction. If it's and then we should say, yeah, basically, if it's some direction, um, okay, so that is nicer. I think that means that basically, as long as we've got any idea what our loop direction is, we're just going to extend the candidates. We don't need to do that anymore. Let's move on. What else do we got in this other walk that we need to remove? So this one, we've done that. We have our direction of travel. Do we have that? Let's just test that. Yeah, we have our direction of travel, which is going to be inferred by this thing. Okay, that's very good. It says something like, oh, that's not good. Okay, we'll let the compiler help us with that. Or you know what? Fuck that shit. Stack of coordinates. And that's not going to be. Yeah, so we've got our pipe, we've got our left and right things, we've got everything that we need to do. This one needs to be collected. So literally just say that dot collect. And why is that unhappy? It says that, yeah, XY iter map on, yeah, we are basically adding everything here. Let's to check. So we're extending this. This might need to, we might need to insane, like, we might need to call dot iter again or something crazy like that, but I'm not gonna bother. Wow, this is terrible code. Terrible, terrible, terrible code. Walking graphs, and like flood filling, everything like that is quite annoying. So we don't need this loop direction anymore. We don't need this one. We don't need this walk anymore. This direction of travel thing is derived the copy trait being moved. Ooh, interesting. Borrow. Notes to check. Direction of travel could be borrowed. Loop direction could be borrowed. Would be borrowed, but doesn't need to because that's the only place we use pipe, and current is also a reference. Probably should be borrowed. Let's try to just compile that. Can't believe this actually compiles. And I can't believe that this actually runs. So let's now debug things because apparently this is somehow still running. So we've got our insight nodes. Let's debug. So we've got dbg. Current, we don't care about the pipe. We do care about the direction of travel. We do care about the loop direction. Let's run that and see what else do we got. And direction of travel is apparently a thing that doesn't have anything interesting on it. So Let's run that again. And it says value borrowed after move. Where's our dbg call? So let's do this. So we start at 1, 2. Direction of travel is south, loop direction is none. Then the next time it should be some counterclockwise. Yeah, that's very good. So we are traveling south, south, south. We hit the corner. We are traveling east. So now we are counterclockwise still. Counter, counter, counter. Where is the clockwise? So this one is not doing the thing that it was supposed to do, which is to figure out that it's now traveling clockwise and not counterclockwise. So let's look at loop direction again. So loop direction, match loop direction. If it's some loop direction, then do this, otherwise not. But also, this one should be inferred. So, oh, wait. But there is no outside, I see. So without any outside nodes, how can we know what our loop direction is? And that is where, let me think about that. Um, hmm. So we should not look at the outside in order to infer our loop direction. We could basically just use. So in this case, we don't need to flood fill anything. We can try to infer that just by looking at the corners and just figuring it out for this point. So that means we don't need to flood fill anything yet. Hmm. Interesting. Now that I think about it, we could have used another thing, which is to color everything in two colors, basically. That could have been also a good way to do this. That is just figure out just have find all the land masses, and each one must be um, wait, do they have to be separate but by at least two, it's the amount of walls that they need to cross? But like let's think about that. So if we've got this thing, so this one is one landmass, this one is the other. Let's pretend we've got another small one here, got this one, and we've got the outside. So if we label this one with 1, and because it's really easy to find the outside, like the outside, the amount of walls we need to cross in order to get into each of these is either one or like it's either even or odd. That might have worked. Interesting. Like we could have just said, oh, here there's like an odd number of walls to cross in order to get to there. Also here we've got like 2 walls, and that's why it's okay. This one is exactly one. So we could have done that. Could have said like how many walls are there between, but that means we need to do like pathfinding, which is hard. Yeah, I'm not sure. I'm not sure. Hmm. So yeah, we need to find the loop direction without the outside thing. So we need to think about that. We are traveling. We've got our bend. Each bend affects the direction of travel. So we are either okay, so when we are traveling, okay, let's look at that. No, we don't need to look on the outside at all. Like, let's pretend we don't need to look at on the outside at all. All we know is our loop direction. Or what we want to infer is our loop direction, basically. Is either now clockwise or counterclockwise. Okay, so we've got, let's match on, we do have our direction of travel, which is either south, like northeast, southwest. And we've got our actual pipe. So let loop direction. So this is actually something that we could literally just do anytime. We don't need to do anything fancy. So let loop direction. We can just infer that. So let's try to match on our pipe and on our direction of travel. Let's try to reason about everything. And then it's either, so this one is actually going to be, we don't need the whole option thing. So, and this one is also no sum. So we just do this. Okay, so loop direction. It's going to be, well, we don't have a lot of options. We do have something, which is, I mean, we've got 4 by something. But the only things that may change the loop direction is are the well the corners, basically. Only corners matter. So we could have this as, okay, so we might want to have this as a mutable thing, because we need to keep track of this. So let mutable thing the option type option loop direction be none. And that is quite suckish, but sure, whatever. So we say match on pipe, then we should say this is a big ass lookup table. So all we know are corners. So basically north, south is, this is going to be some thing. So yeah, this is some direction. And otherwise that's going to be, well, not none, but basically just loop direction. We are just going to retain whatever we had before. So now let's actually do this. So we are, if we are traveling north and we have, this is an actually incompatible corner. So, well, sorry, Copilot, but you fucking suck. So first of all, let's do the direction of travel before. So So we've got, let's do all of the norths, then all of the souths, then, yeah. So travel direction, let's go south first, no, north first. Yeah. And if we're doing this, then yeah, nothing happens. We just preserve the same pipe. That is correct, but also I don't care about this. So let's actually not do that. So what kind of pipes do we have? Do we, when we're traveling north, then we are only supporting pipes that have a south end, which means that's not a lot. We've got southeast and southwest, and south, yeah. So let's think about that. We are going north, then we've got southeast. We are going clockwise now. Then we've got north, southwest. We are going counterclockwise. If we're doing south and northeast, then we are south and north. We are going counter. Northwest, we are going clockwise. East and northwest. If we're traveling east, then we need an east pipe, not. We've got an oh, sorry, wait. We've got a northwest. Yeah, that's okay. So we are traveling east into a northwest pipe. We are going counter. That's our counter thing. We are traveling, if we are traveling east to a southwest pipe, we are going south, which means we are going clockwise. West and northeast. West, northeast, clockwise. Southeast, counter. Anything else preserves loop direction. And then, okay, so as long as we've got a loop direction, we don't need the let thing here. So that's going to be loop direction, just like that. So we can match on that. And as long as we've got our loop direction, and it's some direction, we could borrow it and otherwise we are doing nothing. Okay, so I think that is it on the looping thing. We don't need this anymore. So we just need to say okay at the end. That's way cleaner. So yeah, what we've done so far is we've walked on everything. We've got our pipe loop, we've got outside nodes, which we are flood filling, and we might not even need to do that. We might not need to do any of that. We've got our inside candidates, which are some of them might be like the actual loop. But this is actually just good for our assertion right here. So we've got our inside starting points, and now we can try to run that. That would not compile, of course. Why would that work? It says borrow of moved value. So our direction of travel should be borrowed. Also here. And this one is still not doing well. Shit. Wait, how come we haven't used the left and right thing? Because we shouldn't have? We shouldn't have. We've got our left and right here. Okay, so yeah, that's basically it. We are going to use the direction of travel. We are going to use this loop direction. And we should be able at least to see some clockwise and not just counterclockwise. So let's look for \b clockwise. Okay, so that's at least something. \b. Okay, so we are traveling west. Let's look at that. Our current node is 2, 5. We are traveling west, and we are claiming to be rotating counterclockwise. Clockwise. Is that correct, though? So let's look at the actual map. So 2, 5. 2 is this column. 5 is this one. Wait, what? No. 5 on Y is 1. That's here. 2. 0, 1, 2. 0, 1, 2, 3, 4, 5. How come our direction of travel is considered to be west? That is incorrect. I mean, it is correct that it is clockwise, but how come? Oh, we are traveling west. Okay, never mind. That is correct. That is totally correct. So now we are doing this. And as long as we're clockwise, we should be able to add the right things. So first of all, yeah, that's just running clockwise. And we hit the counterclockwise on node 5, 5, which is probably this one. Yeah, actually correct. So yeah, that's 0, 1, 2, 3, 4. Wait, what? 5. Yeah, that's clockwise. Counter. Yeah, that's where we changed back to counter. Okay, so our thing is doing the thing. We are tracking the clockwise and counterclockwise directions correctly. And then we run, and we should not see counterclockwise ever at this point. Okay, so now that we've got our thing running correctly, we should be able to well, infer the actual candidates. So let's do that. We've got our candidates. We've got nodes to check. So we've got, as long as we're traveling, we've got like this bifurcation thing, but between like left and right. And then it's like left, right, or top, bottom, basically, but should always be correct. So we've got when we are traveling north, and we are counterclockwise. Like, who fucking add? Okay, so basically, what I want to say is instead of nodes to check, let's just debug that actually. This is the thing that we actually came here to do, which is to debug. So let's debug. And then it says something like variants are never constructed. Okay, that's correct, but out 2. Outside, third loop direction. We are not using this. And then it says, oh, panics. Yeah, right. My fault. We should say probably something like dot strip. Let's actually just remove this crap. We've got this thing, and we should say it might be terminated with optional new line, delimited, sorry, with an optional new line. And another optional new line. It probably says that it expects, yeah, and another optional new line. Okay, so now we've got that. Let's look at our nodes to check. Oh my god. Yeah, so this is going to be terribly long, right? So instead of actually looking at that, this should have been like a very small group. So use the import, whatever. We've got this extend clause. Okay, so instead of doing this, let's actually look at our thing here. So let's look at our inside starting points. This is actually a good place to debug. I believe I haven't actually looked at that yet. So we've got our inside starting points is actually let's look at that. We've got 4, 3, 6, 3. So 4, 3. Let's now compare that to the actual map. So this should have been firstly this should have been only 4 coordinates, and the fact that we see more than that is already worrying. So what is 4, 3? 4, 3 is 4, 3 is this one. Yeah, so that's not good. That's definitely not good. Yeah, so the fact that this one exists here is just wrong. So part 2, let's go back into looking at how do we probe into this thing. So nodes to check. This one comes from somewhere. I'm not sure which, but yeah. So we could dbg this thing. So let r be this, then we return r. Just before we return that, we can debug that. So who's offering this thing where we should say probably current? That would give us like the which node is it? And this one should probably .1. Okay, so we've got our current node, which is we should actually look at whatever the thing that so we are unhappy with 5.3, for example. So who added 5.3? So 5.3 was added because of node 6.2. It might maybe was added by more nodes, but let's actually look at that. So it was added by node 4.2, 5.2 itself, 5.2 and 6.2. And if we look at all of these are nodes. Well, here they are. Yeah, so 4.2, 4. So we've got this is line 0, 1, 2, then 0, 1, 2, 3, 4. Then 5.2 is 5.3 is this one. Yeah, so it was added by all of these vertical bars basically. So all of them are incorrect, which means that since all of them are incorrect, wait, let's actually look up 4.3 just because I want to see who adds this one, these ones. So 5.2 also adds it, but I'm more curious about. Okay, so basically when we are when we're traveling east and west, We're still wrong. So let's look at that very closely. Um, left and right. So we've got east-west. We are traveling, in this case, east. So when we're traveling east and we are clockwise, I see. So should we ignore this? I'm not sure. Huh. So the problem is that now that we are inferring this to be a clockwise loop, then we are still looking at the wrong thing. So we should have just kept that. So once we've got that sorted once as a counterclockwise loop, should we just ignore that? Interesting. So notes to check. So loop, direction of travel, and match. Once we set it once, let's try that again. So we set it once as this thing, and we say it's none, then we try to infer it. Otherwise, do nothing. Oh, we can probably also like if we say like a single branch, yeah, if let but let's have that here, just we won't lose it. If let loop equal loop direction, then we want to do all of this crap. Basically, yeah, initialize once now. And let's run that. Then it claims that it's still 12 for some reason. So first of all, loop direction should be only interesting. So we got a bug somewhere because in both cases where we initialize the loop direction once and when we initialize it every time, we keep doing the same mistake, which means that notes to check isn't correct. Let's look at that. So when we are traveling, as we said, east, and we are counterclockwise, we should always take the top. And top is the left thing, and the pipe left east-west top is -1 on the y thing, yeah. And right is the -y. Yeah, this seems okay. So when we are traveling west, the loop is counterclockwise. So basically, oh, maybe this is the problem. This is still left because we still wanted to take the top. Doesn't really matter because the loop it has like this direction generally. Means that also when we are traveling left, we are. I mean, yeah, the loop is still like traveling in like a vague clockwise direction basically, and yeah, that should be the same thing. And that might actually also be correct for the left and right thing. I don't know. Let's try that. Then we've got says, oh, that's not good. Oh, we've got our assertion failing. Inside candidates. Interesting. So we've got a loop direction, like a vague loop direction, but we do want to know whether we are actually traveling. Ooh, hmm. Let's look at that. We've got the vague loop direction. That's the chirality of the loop, basically. Then we do want to know whether we are right now clockwise or counterclockwise. So that is, we need two things, which is the loop chirality and the actual direction of travel, and then we need to invert on that, based on that. That, like, and there's probably like a more efficient way to represent that, but let's do this. So we've got, let's call that loop chirality. Chirality. Rename. Typo, rename to. That, how do you speak? Chirality. Yeah, I think yeah, this is correct. Chirality is a thing. Okay, so we've got loop chirality, which is this thing, and we do have our own direction of travel, which might be something. So firstly, we could say that we could say let loop thing be this thing, and we could have that. And we initialize the loop chirality once, which is to say, it might be none, that's okay, that our travel direction currently is none. Oh, it might be actually the loop chirality. Yeah, basically this is the one. And we say if the loop direction is none, oh, and we could match on the loop chirality itself, which is so then loop chirality is match on itself. Oh, sorry. If let none equal loop chirality, then we need to update that with this thing. That means that basically we update once. As long as it's none, we are updating it. And then we initialize it once, that's it. Now we've got our loop direction and our loop chirality. And when they are opposite, we need to flip. Oh my god, this is terribly terrible. So we've got our match on loop direction. So that's going to be that's going to be literally the else clause of that. So, oh, that's actually not true. Wait. So if let some loop direction, we do this. And we don't need this one anymore. And that is just going to be this thing. And we've got loop direction, but we also need the loop chirality. So this is, let's call that current direction. And that's going to be this one. If let sum equal initialize chirality once. Okay, so we've got our current direction, which is a function of the direction of travel and all pipe. Otherwise, we are taking the loop chirality as the default. And then if we've got some current direction, then we are saying no to check. We need the loop chirality. We've got the current thing. So let's look at that. We've got the loop chirality. And what are we planning to do with that? So let's think about that. So let's of course let's firstly we need to invert basically. So we could say that let direction going to be match on I want to just flip the bit basically. Is it XOR? Not XOR. Let's think about that. So first of all, let's call that now direction. This one is going to be loop. Yeah, let's match on that basically. Match on. Oh, we could match on the Boolean whether they are equal. So it's either loop chirality is equal to this thing. So false. No, that's just not true. Okay. If they are equal, then we do this. Clone. And if they are not equal, then we say yeah, we flip it basically. Okay, so we've got the direction, it is now flipped. That's terrible, terribly terrible. Defined here. Then it says what? As mismatched types, we need to not borrow. What? It says option. Oh shit. Loop chirality needs to be an option. We could say let loop chirality be. Oh, we can just unwrap because we've just done that. We might not. Okay, so we've got an option. Yeah, so we need to do this only if let sum okay, so we got our direction and chirality. So let's just pass them in now. We've got chirality, we've got direction. We want to take a reference and we can compile that. And oh my god, would this fucking leave this alone? No, it won't. Why would it work? Why should anything work at this point? Just sticking around with walking the graph. So we've got this one. If it's equal, then we need to say, oh, sorry, that's going to be this one. It. Direction of travel. God damn it. Okay. Let's rewind and let's do this slowly. So we've got our current direction. We know it to be kind of okay-ish. This is our current direction. Let's try to figure this out. And when it's opposed to the general loop direction, then we need to always flip what we would do on the outside loop. Let's think about that. Okay, so when we've got this thing, we are now traveling clockwise in a counterclockwise loop. So we would want to flip which one of the top and bottom thoughts of the thing we would like to take. And that is when we are traveling west and we are clockwise, we would like to usually take the top. But here we are traveling west, and the loop is counterweight. So this is our general loop. And within that, we've got part where we are traveling west within small clockwise loop. And in this part, in this very small part where we are traveling west, we would like to take the inside of the loop. But usually when we're traveling west and we are counterclockwise with like so, we would like to take the top. But here, because we are inside the loop, we are counterclockwise, like we are opposed to our direction of our natural direction of travel, we would like to take the bottom. Means we would like to invert it when we are opposed to the direction of travel. So let direction be direction be match this thing. So if we are on the same direction as our general loop direction, so let's think about that. When we are against our direction, we would like to do something the opposite. We'd like to do the opposite. So we need to firstly, when we are doing this, we just take the identity because we are correlated, everything's okay. We just wanted to take like when it's true, we just take the loop direction. Otherwise, we take the loop chirality, that's true, or it only flips some of the things, and that's why we get fucked. So let's think about that from all directions, because apparently that's, I mean, we could literally just add this thing here. So let's actually do that. Let's think about all of these very, very slowly. We've got chirality and loop direction. So that's actually okay. I'm gonna split it in two match statements just because it's going to be a little bit more easier to read, follow through maybe. So we've got let's literally just duplicate everything. Stick another loop direction thing here. We've got loop direction clockwise. That is going to be now maybe counterclockwise. And we are missing the loop chirality. And it says that here it's unhappy because of apparently. Oh, so we already got that. By the way, can we just use clockwise like that? Oh, that's nicer. Okay, so oh shit, I see. It's not actually doing the thing. Damn. Not actually like using the enum. Okay, so quite well, quite daunting, but sure. So the first lookup table, when everything is kind of working, so we got our loop is clockwise. Let's look at that. And our direction of travel is clockwise. Then we want to take and we're traveling north. North. We would like to take only the inside. So let's think about that. We would like to take the inside. It's always going to be the right. We are traveling north. We just want to take the right. Yeah. We are traveling north, and the internal thing is now counterclockwise. We'd like to take the left. That's okay. And then Now we're traveling north and it's counterclockwise. We'd like to flip everything, right? And now we're traveling. Let's look at that. We're traveling north and we are counter and counter. We'd like to take the left as well. When we are traveling counter. Wait a minute. Okay. We are traveling north again. The general loop is counterclockwise, but we would like to, but we are traveling clockwise. Means that we would like to take the left. When we're traveling north and let's think about that. So in this case, we'd like to take the left in both cases. Interesting. So that confuses me, and now I think we might want to do something else here. So let's think about that. We are traveling north. In turn, the loop is counterclockwise, but we are clockwise. So that would be equivalent to traveling. Let's just have a small thing here. This is the clockwise thing. We are now traveling counterclockwise internally. So this one is this thing. So we'd like to take the right. Okay, and when traveling south. When we're traveling north, and we are here, we'd still like to take the right. Interesting. Wow, so much crap. South should be probably then left and left. Interesting. So that's a don't care on this thing. And that's a don't care on this one. And moving on, east and west. This one is probably different. So when we are traveling clockwise, we've got this one. We are traveling east, which means to the right. When we are on the same loop direction, we would like to take the bottom is the right thing. And when we are traveling on the opposite, we'd like to take the top, which is this thing. Okay, so I think this is where we've got the opposition, basically. And what else do we got? So west, we are traveling left, and then if we are, the general loop is clockwise, and we are also traveling with it. Traveling west, we are clockwise. We like to take the bottom, which does not make sense to me. Let's think about that. Left, bottom. Yeah. Clockwise. Wait, clockwise is this way. Sorry. So if we're traveling west, it's possible to travel west and get a clockwise thing. Yeah, of course it is. But both things. So we are traveling west as part of a clockwise trip, and we are on the outside loop. We would like to take the top, which is the left thing. And we are now on traveling west. Like the general loop is clockwise, and we are traveling west on an inner counterclockwise loop. That comes here. We would like to take the bottom, which is the right. So in this case, this is what wins. Now, on the other things. So here, let's look at that. So firstly, we know already that when we're traveling north, this doesn't matter. So this one should be left. Doesn't matter what the thing is. Right? When we are traveling north on a counterclockwise loop, generally speaking, we are the general one is counterclockwise. We are traveling north. Even when we are, and let's say we are, yeah, we are still taking the left one. And when we are somehow, yeah, basically, okay, so definitely left. Then that means that also when we're traveling south, that's going to be definitely right. Or not definitely, but I assume now that I'm trying to make sure that we are doing this correctly. And now the east-west things again. So when we are traveling east on a counterclockwise loop, everything is generally spinning in this direction. And the internal loop is now clockwise. When the internal loop is clockwise, we would like to take we're traveling east clockwise, but we're opposite to our general direction. We'd like to take the top left. Then let's look again. So we've got counterclockwise and counterclockwise. So we are now traveling east. If we're traveling east and we are internally counterclockwise. So internally we are doing this. We would like to, no matter what, we'd like to take the top, right? No, we'd like to, wait, a counter east. Wait, we're at the, we are counter. Okay, so where are we traveling east in the cycle? We are traveling east at the bottom. Means we'd like to take the top as well, but it's so hard keeping track of all directions. We are traveling counterclockwise generally. Counter is this loop. Counterclockwise. We are traveling east is right. And we would like to, and actually traveling right. That means we would like to take the quote unquote top. And when we are traveling east clockwise on a counterclockwise loop, we have that here as well. So we are now traveling internally on a clockwise loop. So this is our east now. We'd like to take the top as well. Okay, so what? The counterclockwise. Wow, I'm so confused. We are generally counterclockwise, but we are now within our section here. We definitely want to go to the top. This is now the east one. And now we are on a, okay, so this one should be the right, because right now, if we are traveling counter, that's this one. No, it also should be this thing. Wow, what? Now I feel like I need to debug the first one again. When we are traveling clockwise, and we are traveling east. If we're here, we want up. If we are here, we want up as well. So could have been always up. That doesn't really make sense. At some point this should have been right? So no, sorry, this is bottom. Okay, so both of these, when we're traveling clockwise, this one should have been right, and this one should have been right as well. Because in this case, we are now traveling east. Yeah, we'd like to go down. This is the clockwise loop, and we are going clockwise. And when we are going counterclockwise, we are here. Let's imagine that as an actual thing, just to won't cheat ourselves. So we got this thing. We say so. Okay, so in this case, yeah, this is better to practice on the actual thing. This is now east, and this is west. Okay, so east is when we are clockwise and we are moving counterclockwise. This is counter. When we are moving counterclockwise, we want the bottom. And also here we want the bottom one. And this one, wait, that's its actual direction of travel. Yeah, okay, so bottom all the time. So that should be when the loop direction is clockwise, this one should be bottom all the time, and this one should be top all the time. So let's actually do this correctly. And we've got left, right. Let's also add top, bottom. So Fn top, bottom. This one we takes same thing, returns two vectors. Let's just not do this wrong. So this one is, oh, we need to match on self. So which one is it? East-west is always going to be top, bottom. So yeah, that's the one. Two empty vectors. Okay. Now exactly where to go to. You also need let top, bottom be this thing. And now when we're traveling east, we want the top. No, sorry, bottom and bottom. And also now let's look at things very, very. Okay, so this one also does not care about the actual travel direction, only about the loop chirality. So we could also remove that. So the travel direction might not be even the right thing because we might have like the corners might behave differently. So interesting. So basically for each pipe, instead of like doing the whole top bottom thing, we just want one, which is either top left, bottom right, like all of that, basically. So let's maybe try to formalize that differently, which is to say, we've got function. We want all the like about that. Let's inside nodes. And that is going to depend on self. That is going to depend on our loop direction, which is the virality. And that is going to depend on the direction of travel direction. And now we can match on everything, which is going to be terribly big, but at least we know how to do that. So we can say match on self, virality, travel direction. And that is going to return a vec of coordinates. So we've got pipe. Let's start with east west. East west. Okay, we need more stuff, which is east west and loop clockwise, and we don't care about the direction of travel. We do. So it might be either east or west then, because of course we cannot arrive to this thing from any other direction. So when we are traveling from the east and the loop chirality is clockwise, so we are traveling east, the loop is clockwise, we would like the inside would be the inside, which is the bottom. So that's going to be self bottom. So self bottom is just this thing. Just one vector of coordinates, nothing else. Okay, so remove parentheses, and we could actually remove also the braces. Yeah. Okay, never mind. Then we are traveling west. We would like the top. Yeah, east west. Done. Then we've got pipe north west, south north south. So north south. We are traveling clockwise. Oh, sorry, we are missing the counterclockwise thing. Which is to say, yeah, we just need to flip everything. So this one is now, we are traveling east. We'd like to see this one as well, right? Yeah. Then this is a big ass lookup table. Then we've got north, south. So this one is going to be the, let's actually think this through very, very slowly. So we've got north, south. We are traveling either, we are traveling north. We are clockwise. That means we are here. We want to use our right. So I want basically, okay, so I want self right as a function. And I want here, I want, yeah, so let's actually like have proper functions, and that means we won't need to do like a lot of like manual verification. So we here on this thing, we want to say self bottom, and this one should be self top. Yeah, thank you. This one should be self top. This one should be self bottom. And this one is now we're traveling now south. We would like to take the inside. Yeah, that's the correct chirality. And here we've got north, south, and we are traveling north, but we are counterclockwise. We need to flip. And we need to do that once more. Now, north, yeah, here we need to think again. We are on a northeast corner. We are traveling clockwise. We would like to take the bottom left. Wait, we are traveling north. Okay. We'd like to take the right, basically. Okay, so self right. And northeast. And we are traveling, well, not, wait. We are traveling, we are coming from, yeah, we are coming from the north. Okay, that's okay. That's actually interesting. So, so clockwise plus this thing. Oh, interesting. Yeah, so, oh, a lot of combinations. Have I missed something here? Probably. So the loop direction is clockwise. Could arrive to a northeast corner either from the direction we are traveling from or to. Damn it. Loop chirality. What is happening? Oh, yeah. And basically, okay, so I can tell you what the fuck is going on, basically. We are still counting these ones, like the inside things. Just because like the keeping always to the left or always to the right, something is like not working in the thing. So I'm trying to like keep track of basically like where are we in the cycle, because like it doesn't like when you're traveling here, you're traveling to, let's call that to the east. Then you need to know whether you want to take the top or the bottom, or also here, do you want to take do you want to count the nodes on the right or on the left? So when we're walking the loop, we need to do what? We need to figure out what should we do, basically. But I might like go to sleep basically in a few minutes because I'm very tired and I feel like I'm not focused. But all in all, like we've got the chirality of the loop. The chirality is just the general direction that we're walking is either like clockwise or counterclockwise. We've got like just one option. Like by the way, practically it's counterclockwise. I mean on the small input thing. And we need to basically say whether we want to take, like, if we are now on an east-west pipe and we are traveling generally clockwise, we want to take the bottom or the top of each pipe, basically. Which ones are the inside pipes, basically? The inside nodes. So yeah, I think that's like what I'm doing. I'm not very focused, and it might not have like a lot of value. Some of these things that basically, yeah, I'm just tired. But now I need to. I'll try to finish this. So we've got pipe. If it's a northeast corner, northeast is this one. And then we are generally traveling this way. And we are traveling. So interesting. Not good. Not good. I see problems with my model already. Yeah, I'm not gonna actually win this. I'm gonna destroy this function. Terrible. Everything here is terrible. I'm suffering. So yeah, I haven't really used this one. Not really. Yeah, this is just bottom is just right, and yeah, that's it. Yeah, I'm tired. Nothing here. Yeah, I'm sorry. I'm not. I might not be entertaining after like 6 hours of like trying to debug and think about graphs. Not 6 hours, but only 5 hours and 30 minutes. I might be running low on sugar. Let me try that. Let me reload. So now that I have some more fluids in me and not some more sugars in me, let's try to win this motherfucker. So basically, loop chirality is just the loop direction. Okay, so we've got the loop direction. Let's infer that. We know that once. We just need to, we can initialize it exactly once, which is we've got our direction of travel, like on the starting node, basically. And all we want to say is we are matching on this. And once we've got, okay, so firstly, if let loop direction equals some I don't care. We can just return okay, basically. Or you know what? Some direction. Loop direction. Okay, so we don't care about this. We just need to say let sum I don't care. Return okay. We don't need to do anything. We already inferred the loop direction, like the general direction. Why is that good? Because when we are trying to walk the loop, we need to basically do something. And this is the way to like infer the loop direction, which is basically when we are traveling north and we are seeing something and the pipe is northeast, then we know we are traveling clockwise or counterclockwise. Yeah, just the thing. This is also, by the way, kind of like assuming that the start is not like within a very nested small thing in the loop, but whatever. This is just the heuristic, and I'm gonna flow with that. So otherwise, yeah, we are not doing anything fancy. We've got our loop direction. And that should be also okay, nothing. Okay. Now we need to do another walk on the graph. We don't care about this thing. Oh, we could literally just say loop direction be this, and that's it. Okay, so once we've initialized the loop, we don't do anything in this walk. Now let's do another walk, which is this one. Same graph. Nothing fancy. Basically want to copy this one. And we probably want to say like, okay, something. Yeah. Okay, so what do we want to do in this walk? And this walk on the graph, we need to do something interesting, which is to probe either left or right. Apparently my keyboard is unhappy. A minute. And what does it mean to actually look left or right? It really depends on like where we are and where we are heading. So where would we want to actually go? So let's think about that. So we've got, okay, so what's the actual problem? We just know, let's have a clean slate. We start somewhere, and we know that our general direction is, let's pretend we know what it is. It might be this way, but we still need to somehow, okay, so when we are curving this way, we somehow need to still like keep track of the fact that even if we've got we changed our like looping thing, we just need to keep track on the same like on the same side of this arrow. So how do we keep track of that? Do you have an idea? This is basically like what I've been trying to do, and I'm struggling with like formalizing into a thing. So I need to somehow continue like always go left basically. But left is context dependent, of course, because here we are traveling, let's call that yeah, when we're traveling west, it's like always bottom, always to the bottom. If you can fill while going, by the way, between adjacent pipes, that I think it solves the problem. I'm not sure, because like here we've got like this space is 0 pipes. This area has 0 spaces between it. So we are not continuous between this blob which we're aiming for and this blob which we're aiming for. and we need to somehow not fill up this one. For example, filling going upwards, going upwards through two pipes would be okay. Yes, but what I mean is we've got two ways of going upwards. Interesting. So firstly, the one thing I'm noticing is basically that when we know whether we're going clockwise or counterclockwise, we know exactly that we always need to go basically left. It doesn't really matter. But left is only dependent, and left only depends on the direction of we are. If we're traveling like this, we'll still go left. If we're traveling like this, we'd still go left to that arrow. And also here. Yeah, everything is just opposite because I did clockwise. Yeah, so when we're clockwise, we must go always to the right. When we're counterclockwise, we must always go to the left. And just the only thing that matters is determining this thing. If we do this correctly, then we just need the basic loop chirality. And the only thing that's obviously annoying here is that when we are in like this area, this motherfucking area, this one here, it's still left, but actually, you know what? It's always left. Okay, so always, always, always left, or always, always, always right. So let's figure out if we can actually do this. So we've got our thing, and we know our counter clockwise thing. We know that our loop is counterclockwise or clockwise. That means we must go either always right or always left. So that is going to always respect the and like left and right is dependent on the pipe, not on the pipe, only on the travel direction. So if we're traveling, okay, so yeah, I think I know what we aim to do. So let's edit how we do this. We've got so let's have a function which is let's call that inside nodes. Yeah, I think this is actually okay. I'm quite sure. We've got we must have the loop direction. We must have it because this one only this one determines whether we take the flip or not of each of these. And you know what? We could, instead of doing this or this would make our lives way easier. We could, instead of doing this, we could say this is an array of vectors of size 2, and that means that we are always going to return the same thing. So this is just this way. Oh, come on. I hope this works. Yeah, okay, that's very good. That would help us a lot because that would remove the whole indexing fatigue of doing this with tuples. So here we've got a lot of empty vectors, and that's okay. So we've got left-right things, and that's not exactly right because we also need the top-bottom. So we need function top, bottom, same thing. Come on, Copilot. Oh, so many words without meaning. So we say vector of coordinates, and we are matching on self, and nothing is happening. East west, east west. Are you? Wait, what? Where's our east west thing? Okay, so should definitely have it here. East west should give us, yeah, either top or bottom. And so these are like the top bottom things. Here we've got north south is left right. And let's think about we also want like top left, bottom right, all of that crap. We want to split that into like a lot of small functions. It might be nicer to read that instead of like all of these ugly vectors. So let's actually have that. So we should also have so left right is only north south, and then all of these should be well, top left, bottom right, and bottom right, top right, bottom left. So we should have ELBR, which is the self of not a lot of things. It receives a reference to self, and it should return the same kind of stuff. Copilot is generating too much text, but we are going to use the scaffolding. Then only corners. So which corners actually have like top left and bottom right? So northeast have top left, bottom right. Yeah, that is correct. So northeast. And also southwest. Sorry, southwest, northeast. Yeah, these ones have yeah. I'm not sure this is actually good, but I'm gonna go with the flow. And YABL, top right. Then we should have northwest and southeast. Yeah. So now all we need to do is we don't need to take yet the loop direction, I think. Oh, we should always have like the empty case, which is empty vectors. I'm gonna join a lot of these basically. So we've got all of that. This one should be without anything except for north-south. So this one should be LR. This one should be top bottom. And we are missing the empty vectors. That's very nice. And this one says duplicate code fragment. What? Oh shit. North, south, east, west. So that's not top bottom. That's 0, 0. What? Okay, Copilot is just bullshitting. This is the top. No, this is not the top. So it should be -1, 1, -1, 0, -1, 1, -1. It should be this again. Okay. And let's just verify everything because I can't trust Copilot. So we've got -1. Yeah, we should see a vertical bar, which is, yeah, basically always x -1. We are counting up through y. Here we've got vertical bar on the other side. That's okay. Here we've got bottom right and northeast corner. northeast. Northeast corner should have only a top right corner. So northeast should be here. So northeast should be on, well, that's actually, okay, so top right of a northeast thing should be which one is it? So it's, oh, so that one is the one that depends on the direction of travel, basically. I mean, both of these, but we basically need to either take always the left or always the right. So when we are traveling, is that correct? That's not correct. Interesting. Ah, fuck. So how do we make this work? Shit. Firstly, I don't trust the actual outputs here. So we need to like eradicate them and so fuck. So this one must be also with like some kind of like direction, which is the whole point. So direction. So we've got a travel direction. Yeah. And need to match on self plus this thing. So if we are traveling, okay, so this one is now only corners, and then we need to actually do this. So if it's a northeast corner, and we are traveling, we cannot be traveling north. We must be either traveling either west or south to enter this corner. So this is going to be either pipe north, east. Oh, sorry. We are on either top left, bottom right. Okay. Yeah, we should always basically just have either all left or all right. That's okay. So we just need to do this correctly. So, so northwest. Northwest has a northwest has a bottom right thing or a top left one thing. Okay. So yeah, that is going to be either when we are traveling. So we just might want to flip those around. If we are traveling either east or traveling south or east for this case. So we don't need to match on the direction of travel yet. So we just say northwest. So yeah, that's northwest and that's southwest. So yeah, southwest is not here. So what does this give us? This gives us an array of definitely incorrect crap. So northwest corners give us, what do they give us? Do this very, very slowly. So this should be always the top left corner. So the top left corner is just -1, -1. That's it. This one should be 1, -1, 1, 0, 1, 1, and also should have -1, 1, and -1, 0. And let's just put them in the right order so our eyes won't fall out of their eye holes. So this is the northwest corner. Another corner that has top left, bottom right things are these ones. So this is the southeast. So type southeast. And this one should be either this thing, and to the right it's only one corner, and to the left it's all of these. So let's just make sure that this is actually correct. This should be 1, 1, definitely incorrect, and these ones should be -1, -1, -1, 1, 0, -1, 1, and then 0, -1, and 1, -1. Wow, Copilot is just not doing well at all, but that's okay because neither do I. And we do want to, once we've got that, we do want to flip whatever we're doing based on the travel direction. So we say let thing be this thing, and we should say we should match on the travel direction. And wow, terribly, terribly wrong. So what would mean left? What would mean right here? Sorry, let's think about that. So we want to say something like so we've got this vector, and if we are going through the northwest, so if it's north, so if we are traveling north, then it's only possible for this southeast thing. So left is this area. So this is going to be the whole thing. Wait, southeast is this. Southeast is this thing. Okay, so we are traveling north. That means that right is the small corner, left is the big corner. Okay, that's good. If we're traveling west, then left is a small corner, and that means we need to, yeah, basically flip. So we need to say thing dot jitter dot reverse dot collect. Oh, cannot collect because it's not a vector, it's an array. So how do we make that into build that into the array? We just return thing 1, thing 2. Thing 1, comma, thing 0. Yeah, we basically we need to clone, so whatever. I don't care. Truly, truly don't care. But this one is only valid on southeast corners, so we must also match on our own thing. Wow. Yeah, so these corners are basically just fucking me over. But we'll be there, we'll get there. So this one is now only on pipe south east corners. And that is, yeah, so pipe, yeah, this is the only way for us to actually get there. And here we've got the same thing, but we just need to say, okay, so we've got a northwest corner and we are traveling south. That means that let's right is the small corner and left is the big corner. So when we're traveling south, we need to flip. So let's flip. That's the one where we say flip, yeah. And we need to also have pipe. Northwest. Okay. Oh. Okay. And we do need to do something, which is, yeah, this one, basically. So these are all of the travel directions that are supported on the top left, bottom right graph. Anything else gives us an empty vector. We could literally actually just have none here, then like just not merge anything else. We could say option on that, and that may be a thing. Then it's like and that is and that says why is it, oh, because the thing is not the thing. I see. So first of all, if let something equals thing, then do all of that. Otherwise, we don't do anything. Done. Now that we've got that covered, let's try to do this very, very slowly to all of the others. We've got this. We need our travel direction. And we do want to actually let Copilot help us think it through. Okay. Oh, this is outside of the function thing. So we've got now top right, bottom left. We should have two corners, which are northeast and southwest, which are the exact opposites. So let's actually fill them out and then think about all of these. So we should say something like, oh, by the way, this literally could be match on thing and blah 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 blah, but never mind. So northeast. So northeast. You've got to the by default to the left one thing, and then to the right the yeah Copilot is just not going to help us. So to the left we've got the big triangle, which is -1 thing. Definitely not correct. That's 1 1. So that's going to be again -1 0, then -1 1 0 1 1 1. Yeah. Okay, and that's the northeast corner. Then the southeast corner going to be southwest. So to the left, we've got one thing, which is the minus 1, 1. And we've got minus 1 thing that is just incorrect. So that is just going to be southwest. So 0, minus 1, minus 1, oh, 1, minus 1. And then we should also have minus 1, 0, and minus 1, 1. And that means that we are not, I'm wrong somewhere. That should be 1, 1. Now that we've got our direction of travel, we need to think about things, which is if something, then we match on the direction of travel. We say if we're traveling not only north, but so we are matching on self plus the direction of travel. So we've got pipe northeast. And we've got direction of travel south only. We don't have north, south. And let's think about that. Let's really thoroughly think about that. So we either got, we are northeast, traveling south. Then we would like the left thing to be the small corner. So that means we need to put that, like we need to return that in reverse. So so that would be the sum array, which flips everything. Then we've got if we are traveling west, then we should say that left is this thing, it's this big corner, and yeah, that's okay. And then we have more things, because if we are on southwest and we are traveling southwest, we are traveling north, we would like to return left is going to be the small corner. So that would be the flipped array. And if it's the east, then to our left is the big corner, which is the index 0, and that's okay. Okay, so this one is done. We just need to return also like this thing, yeah. And okay, moving on. Left, right, top, bottom. So also here we should do the same thing where we say the direction of travel actually matters. So travel direction, also this thing. All of these should have been borrows, but whatever. Yeah, let's fix that quickly. So how would we do this? We should literally just match on self plus that because there's no need for us to like for just one case. So self, comma, travel direction, and that should be now either travel direction. So north south. If we're traveling south, then so if we are traveling south, what would be considered always left? So traveling south considered always left is going to be the well, actually the right one. So we should flip. So let's actually first of all do north. Then we should just copy that to say south, flip. And let's just make sure that this is correct. When we are traveling south, we would like to say that the left of us is index 1. Yeah. And same thing here. So we could Copy that, move it here, match on both. And then we should wrap that into an enum, travel direction. Sorry, travel direction east. Then let's think about that. We are now traveling east. To our left is the top, which is -1 on the y-axis. That's okay. Then we should duplicate, go west, and then to our left is the flip side. So we've got our top, bottom, left, right, top, right. Yeah, okay. So each each pipe type has its own thing here. And all of these always return an empty vector. These ones return an option, which means that let's actually also convert these to return an option. Then we could merge everything. So this one should return, these ones should return something, and none. And also here, this should be none. And this should be an option. So everything here now returns options. The only thing we could try to do is actually like make these like the same, behave all the same way, but doesn't really matter. But no more empty vectors, basically. Either returning the right thing or not. So now all that we're missing is basically what should we check, left or right? And that is a function of the loop direction, the general loop direction, and the direction we're traveling right now, and the thing. Which means that we should have like the next, not next, nodes to check. These are going to, this is now going to be like the reference to self. This is going to need a loop direction generally because we've got either left or right direction. That's going to be why am I not seeing this? Let's just have literally just a left, which is a bool for now. And we do have our travel direction. Function. Nodes to check. Auto completions just didn't work for a minute, so I just wanted to like use ref self, loop direction, and travel direction. Okay, and this one should return a single vector of coordinates. Now we can actually do this, which is going to be a lot of things. So yeah, I think that is it. And now that I'm looking at it, all of these are basically non-overlapping, which means that we could like merge them into a big ass switch match statement. We would just need to somehow understand later, like what did we mean, and actually merging them might be a little bit nicer. So let mute vector nodes to check. That's going to be an extend of either 1 or 2. No, so this is definitely incorrect. So let index going to be match on loop direction, clockwise or counterclockwise? Yeah, either always left or always right. And that's going to be an I size in a minute. We're going to do that. So index and no need to clone. And we cannot move. Shit. And dot iter. Okay, seems legit. So basically, this means that we are now extending by everything. Yeah, we're basically collecting everything into like one big ass vector. We could also literally just, I think, flat map that. That might be a thing. Like flat map on like map filter map. That might be actually like nicer. So like nodes b, let's literally collect that into a vec. But I think that would be nicer. And that is now we can literally just filter. So filter OK, I think, or filter. Let's think about that. So filter map, basically. And dot x collect. I think that is it. And we don't even need to let it know what this collect is for now, because this is all the things that we needed to say. So these are all the nodes. Oh, we could literally. Oh, interesting. Let's actually do this match nicely, nicer. So we've got our x, which is something, and it's either, yeah, at the place of index or none. And we do need a flat map that. So that's going to be flat map. Oh, sorry, flat map here. Oh, so that means we don't need to do this right now. So we can just filter on those that are none, basically. So yeah, this is basically now a vector of coordinates, and we do want to just say index dot iter. And why is that not working? So this is our vector. This is, consider giving it an explicit type. This is going to be a vector of coordinates. And this collect is going to actually complain, but this is now going to give us like nicer types. So, oh, we could literally just return that. So, okay, no need to use this. And let's actually look at that. So we say flat map. We're returning the iterator of node. Oh, I see. Cloned. That's it. Yeah, we needed to clone the coordinates instead of like returning a reference. Okay, so these are all the nodes that we need to check, given that we are either going all left or all right. Okay, let's try to use this. So run part 2. So we could walk and add all of these nodes. So all we need to do to know is we do need to infer our loop direction, which we've done right here. Now we need to infer direction of travel in this walk. So this one is actually, yeah, we need to open that up. We need to say let type direction of travel be this one, whatever this is. Yeah. And we do want to do something about all of all of these things that we just did. So we just want to say inside candidates, extend pipe nodes to check. Okay, let's just do this slowly. So firstly, we do have our loop direction. Oh, so yeah, let loop direction, okay, all unable to infer loop direction, that's good. So we've got our direction of travel, we've got our loop direction, and we've got our, for each pipe, we know what we need to do. We need to say candidates, and we just need to extend them. So yeah, that should do it. Now let's run that. This won't compile, of course, but ooh, all of this needs to be deleted. That's very nice. Yeah, all of that can be just removed and destroyed from the face of the earth. And next up, what is this? Notes to check. Oh, that's actually important. It says not move out of X because of a shared reference. So it does not implement copy. So how do we flatten that correctly? We could do this. And that is now going to be just X cloned. And would that work? Or do we need to like dereference that now? So this is still an option. Interesting. So let's do the match. So we've got match on X and X. If it's something, then we say X and X clone or just iter. That's good enough for now. And otherwise it's none. And let's try to compile that. Ooh, seems to be compiling. Seems to be compiling. And we've got panicking. Ooh, outside nodes contains coordinates. Shit. So we've got an assertion that protects us, and let's add debug statements and figure out what went wrong. So we've got nodes to check. So let's debug our candidates. So dbg. Would this work? This would not work. Of course it would. Would it be? dbg candidates. And we would like to also dbg the current node. So that would give us like an idea of like what the fuck happened. Oh wow, that's a lot of things. So the start node, we are saying the candidates are -1, -1. Oh, that's already bad. So is everything like flipped? We just need to flip the bit and that would maybe work. So it's clockwise. We need to take this one and then this assertion. Yeah, okay, so no, I just have a bug, an actual bug. It's not going to be an easy win as this one. So let's assume oh, I want the direction of travel as well, just to be like complete. So we've got the current node, direction of travel. Actually, the pipe might be even better than the current node. So yeah, pipe direction of travel. Okay. So we've got pipe north-south, direction of travel south. And we are getting the opposite of what we wanted. And why is that? By the way, DBG, loop direction. Counterclockwise, which is correct. Okay, so we are traveling south. We would always like to go now, if this is the loop that we are doing, we will always like to go left. So let's go left. Let's make sure that we are always going left. So counterclockwise actually needs to go always left, which means this is the 1, this is the 2. And now let's look at that again. So we've got 1 now on the x-axis, that's okay. 2, northwest, still okay. Current 1, 4. We could also like actually look at the test, but I kind of like already remember some of it by heart. So as long as we're going northwest, everything looks fine. Direction of travel south, then we are hitting the northeast corner. That's the northeast corner. That's the L. We are still coming south. That means we would like to only take the. Ooh, interesting. So there's a bug. So northeast corners should have the 1 minus 1 thing. So let's go to the northeast corner and fix that. Northeast. So northeast corners have a top right, and it is definitely not a top right one. So that would be a -1. That's just a bug. An honest to God bug. Southwest. Let's continue on. So our southwest is going to be, let's just make sure everything's okay. So southwest has a -1, 1. That seems to be more sane. Okay, let's just run that and see if like things are better. So first of all, we are still leaking things outside, so that's not good. But we do know. Oh, we could literally. Yeah, okay, this is the northeast one. Yeah. So now this is still like supposedly correct. Then we say current equals. Oh, I know what exactly have I done wrong. I'm missing one important piece, which is back to this thing. So all of these candidates are very nice, but they're not actually, well, you need to add the current coordinates to them. These are just the +1, -1 things, not the actual thing. So this needs to be mapped onto adding the current +1, -1. Yeah. Would these be a little bit better? So we've got current. Oh, now this expression is like terribly long. So let's DBG that out of everything. So we could say this iter map thing. Okay, so we've got our iter map thing, and this should now be a little bit nicer. Oh, we probably should collect that. Classic. And we need to do this. And this won't compile because it doesn't know what to do. Oh, we could actually leave that as an iterator. That could also work. And why would that work? Because we just extend that through an iterator. So it might just work. Temporary valued freed. Wait, what? Temporary value is freed at the end of the statement. Type. Type dbg. Oh, is that a problem? So candidates. Type nodes, blah, 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 blah. Let candidates equal binding. Fuck that. Let's just collect that into a vector. Okay, now we've got actual coordinates and um, not offsets. It might be a little bit harder to read, but it would be the ones that we actually wanted to do. By the way, we still have nodes that are outside, which means that we might still have bugs like in the offsets that we computed. So let's look at that. So we started with the, let's find the first northeast. So that's the one. Okay, so far we've been to this thing. So we are here on x equals 6, and that equals 2, and our, oh, that's still, yeah, current, okay. So 2, 7, yeah, that's correct. We were traveling south, we got to this corner, now we're currently on this one, and our new candidates are x equals 1, y equals 6. So this one is correct, yeah? Okay, so we're looking at the top correctly. Moving on. So east-west should be also correct, and it is, I think, yeah. Our current now is going to be a northwest one, and let's look at that, and we see that we are looking on the wrong side of this tube. Okay, so we should be looking left, and we are looking right, which means that we need to flip the direction of the thing in the enum. So northwest, here we should say flip. And let's reason through that. We are traveling like so. We would like to look at the left, and the left is the corner. And we could have either done that by looking here and seeing that we are. Yeah, okay, so this is actually, let's actually do this correctly. Let's match on the full enum. So that's going to be match on the travel direction as well as the self. And when we are traveling east, travel direction east, then this is our left. So wait, what? Let's think about that. Sorry. So when we are traveling on a northwest pipe, that should be to the left of us is this one, is this corner. But then we should flip things, right? Because this is what we have, or wait a minute. In our counterclockwise, this one should have offset 0. Interesting. So we need to think, I need to meditate on that for a second. Offset 0 means that this one is the left one. Yeah, that is actually counterclockwise. Yeah, okay, so left one is, no, left one is the corner. Yeah, okay, this is the right one. Okay. Northwest, small corner on the on the thing. Okay, now we've got travel direction east. And we should have the same thing, but travel direction west. So we duplicate that, and we flip the thing, and we flip this to be south. And now to the left of us, when we are traveling, it's the big corner. Moving on. Oh my god. Southeast should be. Let's look at that. When we are traveling southeast, this should be north. And let's first let's understand this should be east now. And there's no need for the whole left thing here anymore. We just turn the match, just like that. And southeast traveling north. So southeast corner is this one. We are traveling north. To the left of us should be a small corner. Southeast, we are traveling east. To the left of us should be a big corner. Okay. And this one is actual, but wait. Because we should be flipping things around when we are clockwise or counterclockwise. So when we are basically traveling counterclockwise, does that matter? Yeah, okay, it's all about whether we want to basically just take the left or right things. So to the left of us, this is just to the left of us is always and the southeast corner is going to southeast corner. That's going to be a small thing. Yeah, a small corner. Okay. Wow. Hard to reason about, but allegedly simple. So we've got where do we where have we got at this point? So this one is east-west. East-west are these ones, and then we should be traveling upwards towards another east-west. Let's look at that. So these ones should be x5, y, what? So current, 6-2. 6-2 is this one or this one? 2. 6-2. So east-west, direction of travel, east. Candidates. 5-1. So 5, that's x5. What? X5 or east-west? Oh, sorry. That's the east-west. I see. I've skipped too many. Sorry. East-west, 3-5. Let's look at that. 3-5 is somewhere. Okay, we need to backtrack a bit further to make sure everything's looking kosher. Yeah, 7-2. That's the one. Okay, so we've got east-west. We are traveling east. That is correct. Then we are seeing x1 to all of them in row 6, which is row 6. 0, 1, 2, 3, 4, 5, 6. Great. Then east-west current, another one that should be not surprising. Yeah. Northwest, that's the one that's important. Then we should see 3-6. That's amazing. Current 6-4 should be north-south. Traveling north should be, we should always be on the left, which means it's column 3. That's great. And then current 5-4 should be southwest. Traveling north should be a small corner, just one corner, and it isn't. Okay, so that's the next one. So southwest. So southwest on the left should be, yeah, and that's the one where we are haven't actually fixed the enum, and this is where we are having bugs. So probably due to my fault. So travel direction. But I feel like we're getting closer. So first of all, yeah, we've got that. So northeast, so we should be able to either travel south or travel west. And which one of them has, okay, so no, if it's a northeast corner and we are traveling south, to our left is the small thing. And if we are northeast again. We are traveling west. To our left is the big thing. Okay, that seems to be making sense. And now also let's go with this one. So southwest is only possible when we are traveling north. And when we are southwest, we are traveling north. To our left is, wait, southwest. That's the one. We are traveling north. To our left is a small corner. And that means that the only thing that's left is the traveling east. And to our left is going to be the big triangle. Now we can delete the semicolon, remove this let thing, and delete whatever comes after this one. And they're almost done, I think. So first of all, we are done with our assertions, which is quite amazing. Now, all we've got to say is we just need to see that we are not leaking things like for the internal one. Slowly, but we're getting there. So where are we? Let's go back to looking at this beautiful, beautiful maze. So we were at what was it? Southwest, right? Southwest, yeah. Southwest. That's the one, 6-3. Yeah, seems to be reasonable. Traveling north, should see one corner. That's correct. Then we walk, and we see that we are traveling west, and we've got an east-west, and we are looking down on the same three things here. That's okay. Then we go for northeast, and again we are. I fucked this over because this one should have been just one corner, and it is all of. Oh, okay. Actually, that's correct. That is the big corner. That's good. Then we've got north-south. We should be seeing, yeah, the vertical pipe to the left. That's okay. Then north-south, southeast. Southeast, we should see, oh, that is incorrect. We are traveling north, southeast. Should have had the big triangle, and instead of that, we've got the small corner, and that's why we are flooding this thing. So southeast. Let's look at that. We are traveling north. To the left of us is the big thing. And if we were traveling east, to the left of us would be the small corner. And we run that again. And the test pass. Ooh, interesting. So now that we've got that ready, let's run that over the thing, the actual like input. That took way too long. And we've done that, and I forgot to obviously turn off debug prints, and then we've got some number, and that number is feeling like it's way too high, but one gold star. Yes! Wow. It just took meticulous work and being a little bit more focused. Wow. Oh my god. Wow. Oh my god. I'm gonna sleep. Bye. But I had fun. I had fun even though I'm like way too tired for this shit.